Morning, everybody. How are you doing today? Good. Oh, such high energy already. Well, we are going to start our first session of the day on placement procedures. And with that, I'm going to pass it over to Bill and Steve to take you through that.
I'm Bill Rickard, and I'm a drilling engineer. I'm Bill Rickard, and I'm a drilling engineer with Geothermal Resource Group. I turn it over to Steve.
I'm a consulting drilling engineer, and we're glad to see you here for this placement procedures talk. Placement procedures are where we have the high risk of a very expensive failure, and as a committee chairman, I tried to recruit people to talk about their failures, and as you will notice, I was totally unsuccessful. Nobody wants to talk about their failures. And so if anybody has any great ideas how to recruit operators to talk about their failures, it would be very helpful. Our first speaker today is Rafael Hernandez. He'll be talking about proper centralization for optimum cement coverage and long-term wellbore integrity in hot and corrosive drilling environments. Rafael, if you could give a little bio before you start your talk, that would be appreciated. Thanks.
Morning, everyone. So I'm Rafael Hernandez, and my old joke is I'm the guy that doesn't look like his name. So the one thing I want to talk about is well, just to introduce myself, I've been in the industry for about 23 years, primarily mixing, pumping, and bumping, that is cementing. And now I'm more focused on casing accessories. So worked in geothermal for at least 10 to 12 years of those in several capacities, primarily in Western US and overseas. As a matter of fact, I think last time I saw Steve was in New Zealand. Anyway, and Sam might have been in Indonesia. I don't see Sam today this morning here. Anyway, so let's get started. So what's the relevance of proper centralization in this case that we're going to discuss here? Yeah. The relevance is that, like I said earlier, it's rather neglected. We tend to focus on developing exotic slurries, selecting exotic tubulars, super seal, not super seal, but super duplex stainless steels and high-end threads from Gabriel's group here. And we focus on highly specialized slurries, right? Diffusivity properties, enhanced mechanical properties, rheological hierarchy, and a lot of stuff. We do a lot of finite element analysis. Ask Nicholas here. We look at different slurry, our zonal isolation components and alternatives in the Portland and non-Portland world. Ask Daniel Boer about that. But the one thing that you did not notice that was not evident from Daniel's presentation or Nicholas' presentations, two presentations that come to mind, is that there is an assumption in what they do. And the assumption is that the tubulars are concentric. So Daniel said, well, I recommend this product, but make sure it's a 13.5 or 13/3 by 17.5 inch hole. Well, what if it's eccentric, stuck on one side? So anyway, with that train of thought, let's mention a little bit about what's the impact of centralization when it comes to casing run. So zonal isolation and all those items that we're going to be covering briefly. Cement coverage, stress forces, which is critical, and we'll probably emphasize a little bit more on that one. Gas migration, anyone? Corrosion, CO2 attack, and in general, potential issues. And then I'm going to end up the presentation with what are the main reasons not to centralize. So here we go. So for casing run, torque and drag could be an issue, but you should, where's John with Pegasus? Let's simulate centralization. Let's simulate torque and drag to select the proper centralization method, placement, and technique to minimize torque and drag, to optimize run downhole. Proper clearance in the annulus between your tubular and your hole, whether it's casing and casing or bare hole. Let's help optimize fluid velocities to remove all the cuttings. And let's minimize differential sticking. Larger area, casing against the wall of your formation, you could get stuck. If you have centralizer blades, less area, less prone to getting stuck from a differential perspective. Zonal isolation. Yeah, we talk about that a lot. We're looking for that. That's key to long-term wellbore integrity. Cement coverage. If you don't have a properly centralized system, chances are your cement is going to want to go the path of least resistance first. So I was explaining this to my children, and intuitively, they thought that the narrower annular side would have the higher velocity because it's narrow. Turns out, because it's narrow, fluid does not want to flow through the narrow path, rather go through the wider path. So you can end up in a scenario like the one depicted here where you don't have 100% cement coverage. So, all right, I don't have 100% cement coverage, but I pump 30% excess cement, maybe 50% excess cement to cover anything that could happen, potential losses in top of cements. But in some scenarios, it's critical to know where your top of cement is. Again, ask John over there again. What if it's a liner and you go volumetrically? You pumped X amount of barrels in, X amount of barrels return. You're happy because volumetrically, nothing was lost. But you may have one side of your liner fully covered or over covered, and the other side may not necessarily be covered. So if you look at this simulation here, aside from the diffusivity of the fluids that causes the change in color, on the left side, it seems like if that were a liner, maybe that side of the liner, if that were a shot from one of the angles of the 360 degree circumference, you see that, well, one side did not make it to where it's supposed to. On the other side, no issues, because we had a fully engineered slurry design, and diffusivity was not that bad. Flow regimes were great. So you got full coverage. Everybody's happy. So let's say we have full coverage. We log the well. Everything looks good. Everybody's excited, full coverage everywhere. So there is zonal isolation, fair enough. But what about when you induce, just the nature of the beast, thermal stresses, pressure stress? I got full coverage. But where do you think the maximum stress is going to occur? Well, where there's less mass of cement. So the thinner the sheath, the more prone to failure. The thinner the sheath, the more prone to acid attack, CO2 corrosion, CO2 attack, whether it's carbonic acid or supercritical CO2. And of course, as your tubulars expand and contract because of the effect of thermal induction, it's also going to fail or want to fail on the thinner side, which is, if I may, the path of least resistance for damage as well. So when it comes to CO2 attack, regardless of the slurry design, again, you may have the best slurry design. And we saw a couple interesting presentations regarding slurry designs. Still, the distance from your wellbore to the tubular is shorter on the shorter side. So it's going to corrode faster on that side. Intuitively, also, the annular gas flow is going to cause a larger impact on the thinner side as well. Now, I don't remember exactly the equation, Daniel, but you take into account the difference between both diameters of the pipe and your hole. So if your hole is 17 and a half and your pipe is 13/3/8, you use that difference diameter, you call it effective diameter, to calculate your flow potential. That'll give you a number, assuming static gel strengths and other stuff, the length of the column. But my point is, mathematically, 17 and a half minus 13/3/8 is what you use to calculate your flow potential. But what if it's eccentric, like in this case? Larger diameter minus smaller diameter is still the same number no matter what. But on the lower side or the thinner side of your annulus, your gas flow potential is higher, period. You normally don't average out your diameter distances, and the assumption in a linear equation is larger diameter minus smaller diameter. So just to kind of summarize in a bit, the relevance of centralization, maximum stress, and standoff is that if you look at the x-axis, 100% centralization is going to have the lowest maximum stress. And the lowest standoff, closer to zero. I don't know why I'm stuttering so much this morning. I was pretty fluent yesterday. You're going to get the highest maximum stress in your cement system, whether that is done empirically or whether that's done through finite element analysis. That's what you're going to see. There's a red dot. All dots are red, by the way, but there's the one red dot between 60 and 80, closer to 70 rather. That's the recommended standoff that API preaches, 67% standoff. If you're within that region, yeah, your maximum stress is not brutally alterated and the impact is really minimum. You don't have to try to have 100% standoff. That's what they're saying. 67%, that vicinity should be considered good standoff, should allow full coverage, should allow minimum stresses in your wellbore, should allow minimum ability for chemical attack, CO2 attack, etc. So if you're within that number, you're good. Something that we as centralization people don't necessarily mention is that the better the standoff, that is the closer to 100%, the higher the ECD in your system. So if you're also trying to combat or lower ECDs to minimize losses, the better it's centralized, the higher your ECDs. That's just from a hydraulic geometry perspective. If you throw in the volume that these, depending on the style of the centralizer, occupy, so now you're inducing a higher drag forces. If you want to get technical, you're increasing your skin drag and your form drag, but there's ways to mitigate that. The bottom line is centralize, because you invest a lot of money, time, and resources in coming up with the best slurry design for the challenge you have at hand. But then when it comes to centralizers, we either don't talk about it, don't necessarily engineer the placement of these centralizers. And in many cases, all you're going to hear is, I'll run one every other joint. Oh, you know what? Put 2 at the shoe and the rest every other joint. And we start looking at just rules of thumb to place centralizers when it's critical for long-term wellbore integrity. So the issues are, if you don't properly centralize, just kind of to summarize here, sustained casing pressure, wellhead growth, that's another one. If the cement doesn't bond well or the sheath is too thin, everything is less in magnitude. So chances are your casing may grow. I know you can pre-stretch casing. We used to sandblast the shoe track, do all kinds of tricks to minimize casing growth or wellhead growth, but it still happens, and with improper centralization, it's exacerbated. Obviously, the lack of a proper cement sheath, you can eventually collapse your tubulars if there's water or naturally occurring brines trapped in that void. Then you cook it off with high temperature, you could collapse your tubulars. Nobody ever saw that in Hawaii, Dan or Mark or Bill, right? But it may happen. Casing degradation, obviously, from a chemical and corrosion attack perspective, like I mentioned earlier, mist top of cement. For liner applications in particular, that's critical, that you want to make sure you got your cement coverage where it has to be. At the end of the day, cement failure is what needs to be avoided. So what are the main reasons why you do not want to run centralizers in your wellbore? Oh, my well's vertical. I don't need centralizers. Casing collars are my centralizers. These are anecdotal responses. When I met with customers, they announced this, and I was the only one in the room laughing. They were serious about this. So my wellbore is vertical. I don't need centralizers. Casing collars are my centralizers for those that run API and TNC type tubulars. I don't want to get stuck. Another solid argument for not running centralizers. I don't need them. That's the most common one. Oh, well, I'm going to rotate. Everybody has a rotating head nowadays. I'm going to rotate. No need to centralize. Well, stop rotating, and what happens to your casing? It's going to stop somewhere, right? Maybe against the wall of your wellbore. They're too expensive. Here we are running carbon steel with exotic threads, super duplex stainless steel, titanium, and now we're worried about a $30 centralizer, and all we need is 50. And this is another one that I hear for those that understand how the impact is on ECD as well. It's going to increase my ECDs. Yeah, if it increases your ECDs, manage it. It's not going to increase it in one order of magnitude either, but manage it. So that's all I have. Thank you.
Okay, we have time for questions.
Thank you. Very interesting talk. I've looked at a lot of logs, and it's easy to see where casings are not centralized and lying against the formation or a previous string. So I fully support the fact that we need to put more centralizers on casing. What is the best way to calculate how many centralizers are needed?
Well, in general, most major service companies have pretty well-developed centralization systems, programs, simulators that take into account running forces, restoring forces, placement, sag of the casing, depending on casing grade, weight. Others are going as far as looking at rotating pipe in their simulations, looking at affixing centralizers to their simulation, in the simulation, looking at centralizers that rotate freely. So that's a question for John here, and where the Schlumberger guys. They probably have they could probably give you a better answer to that, but it can be simulated with all the right parameters for input. You can get an optimized solution for centralization type and placement.
Yeah, I agree with that. John just bailed me out just a week or so ago. I needed to run centralization program, so I utilize their software as an independent consultant. I know that Halliburton, Schlumberger, the other majors typically have centralization programs. So they're very important to have on critical wells, and every well, geothermal well is a critical well. My comment and or question is about the impact of contaminated cement. Again, I just got back from a job where if casing wasn't properly centralized, and I was showing over 1,000 feet of overshoot on the high side, on the wide gap versus the low side. Comment or question is just, there's a lot of contamination that occurs, a lot more when you're not centralized. So I think that's something you could maybe add to it, or at least needs to be commented on.
Yeah, I could probably have that to my presentation, and definitely, like I said earlier, we normally focus on rheological hierarchies and diffusivity among fluids and flow regimes, and we want to achieve turbulent flow if possible. Others prefer the laminar flow route. We want to increase the apparent viscosity of our fluids just to aid the clean out. From a mechanical perspective, we also focus on chemical changes in our systems to remove and clean better, but then we run a centralizer, one every other joint at best, or don't run any at all.
Rafael, what about a preference between rigid, bowspring, or turbos? Do you have any preference there?
Yeah, the turbo does the turbo only in simulations at best, and that's assuming full concentricity. You really don't get more, and in all the data I've seen, not more than a foot downstream of your turbolizer. You may get a deflection in the path, but you don't get truly induced turbulent flow with eddies and vortices and all the fun stuff that you need.
So don't waste our money on turbos.
To me, those are gimmicky, but I have them if you need them. Now, the solid centralizer, one of the issues with the solid centralizer is the fact that they don't contract and you know, they do not deflect. So unforeseen changes in the wellbore restrictions, that could be an issue. Plus, just the mass alone may add some weight to your system. The front area is typically very high, so it induces, even though, let me back up a little bit, even though some providers may claim that their solid bodies have a lower friction coefficient, well, the most popular Tesla model has a lower friction coefficient than the Jeep Grand Cherokee, but it's taller, has a bigger head. So which one produces more drag? The Tesla, not the Jeep. So my point is, just because it has a lower friction, typically they have a lot more mass to them. So there's a lot more restriction in the annulus as you flow or as you run in, hence more drag. And if we remember, which we normally don't, that drag is related to the velocity squared, it causes a huge impact. So I would go with the bowspring in general.
Thank you. I must actually disagree on that part, because in deviated wells and horizontal wells, bowsprings have actually almost no effect to support the casing. They are not strong enough and they can't do the supporting of the casing. By using rigid stabilizers, at least you achieve a minimum constant, if you want, standoff in the system, which allow you at least to have something that you can use for calculations. Whereas most of the bowsprings, if you really want to do that for a 30-foot casing in a horizontal well, you will need probably 3 or 4 bowsprings centralizers on that because of the weight of the casing. So probably the solid centralizers will be really the options that you have there. Because from my experience, we are always looking on the bowspring centralizers to be very strong, but a strong centralizer means that you have to push it hard to the formation. And the restoring force as well as the running force, sometimes we are confusing them that they have to be as strong as possible, which is not true.
Well, I disagree with you, and this is because if you run a well-designed bowspring centralizer that is not welded, that is a single piece, that is designed to go in a horizontal section, that is run at gauge, that is that it has a zero run force as you're introducing it or starting in running force, and the restoring force is sufficiently strong if you consider a single piece or a solid body having basically an infinite restoring force because it doesn't flex. If you look at a competent single piece centralizer, bowspring with less flow area, the fact that it does have deflection in the bows means that it's less prone to drag and dig rather into the formation. It'll tend to bobsled better than a solid blade that tends to, if it's a straight blade, this is all based on my data. If it's a straight blade, it tends to dig in the hole. If it's a turbolizer type centralizer with spiral blades, anybody has seen how we plow snow? You're plowing your well bore on the low inside. And when you're running heavier fluids inside the casing, it makes it even worse. So I'm not a fan of solid centralizers, but I do sell them. And they have applications in many cases, but for the most part, I would go with the bowspring centralizer, properly designed, not the cheap welded one.
One more question.
Yeah, thank you very much. Just a quick one, and you probably just answered it, but I agree on the bowsprings. Maybe they need to change the name because there's a conception that bowsprings, especially under ultra high temperature, are not robust enough for the applications. So will you address that?
Yeah, there's a new generation, well, it's rather new generation of bowspring centralizer that are made by a single piece of steel. They're laser cut, and they have basically boron in their system that make the metal, gives the metal certain properties that we all enjoy when we run in the well bore, especially horizontal wells. The other thing we're doing as an industry is looking at the coating of these centralizers. Some of these paints enhance the properties, especially reducing friction and drag. The geometry of the bow, some have like a bevel rather. And there's changes in that technology that we've seen a major contribution to running in the hole and providing adequate standoff while still having the ability to pass through restrictions. The other thing we're doing with metal centralizers in general is with special coatings for applications where there's naturally occurring brine. Does that sound geothermal? Or there's exotic casing tubulars. Well, there's a phenomena that we also tend to neglect, which is corrosion between dissimilar metals. That's called galvanic corrosion, right? You have one type of metal on your centralizer. You have you have the exotic stainless steel or something else. You have temperature and you have a naturally occurring brine. You have a reaction. So there's also polymeric centralizers that mitigate that. There's also all kinds of technologies that you can use. But back to the solid bodies, if they're metal, they're heavy, and they're tricky to run, despite the fact that they have no running force, and you have to run them under gauge, otherwise they won't pass your tubulars. A bowspring you can run at gauge, And if anything unaccounted for, they're going to flex. So those are the few things that are worth considering.
Okay.
And real quick, back on the polymers, if you run polymers, those things, they shave like Parmesan cheese. The blades wear. I don't care if they're fiber reinforced, if they're phenolic based, if they're any kind of plastic, they're prone to shave. As a matter of fact, we used to call them the Houdinis because you run them in the hole and when you get stuck and you need to pull out, they're gone. Thank you.
Thank you. We have some comments online from Oliver Coker. Thanks for the talk. Right on. I do failure analysis of geothermal wells. The #1 failure root cause I have found over the past few years, a void in the cement leading to trapped annular pressure, leading to partial or full collapse, corrosion, etc. Over a field of 12 plus wells in J block, solid centralizers provided better running, better cement bond block, better centralization, and fewer channels than the best bowstring centralizers. Facts, not opinions. So personally, when I'm running a string of pipe, I run bowstring centralizers in the open hole and I run solid centralizers in the casing by casing annulus. And I think I'm getting the best of both worlds. Will asked me to mention that there's food left out there if anybody wants food. Thank you very much, Raphael. I certainly appreciate it. Our next speaker is Afsan Ahmadi. And you'll have to share your screen, I believe.
Hi, everyone. Just give me a second to share my screen here. Saying you cannot start a screen share.
I just did something.
Okay. Oh, perfect.
So all we see right there, you go.
So let's change it to. And let's switch the slide here. Okay. Can everyone see my screen here? So can you see my screen?
Yes, we can.
Okay, perfect. Yeah. Okay, thanks everyone. My name is Afshin Ahmadi. I'm working with Halliburton currently in the Halliburton cementing. I started with Halliburton in 2012. Before that, I was working in petrochemical industries for 7-8 years. And I started in Canada for like 8 years now. I'm helping the US in North and South Dakota, just doing engineering stuff. Sometimes I'm just helping a global team for some other tasks. So the topic I'm going to talk about today is thermal low rheology variable density cement design. That was done for Shell in Canada when they were planning to extend the lateral and slightly reducing the annular size. So this is the case history out of tons of job, and the result we will be reviewing in the next slides. So the issue and background in general, with advancement in the drilling technology, we could see all the operators, they're trying to extend the lateral and to cover more formation to increase the production. And at the same time, they're reducing the annular, or let's say open hole size, and the annular cross section is getting tinier and tinier. So the challenges with cement, you're going to end up with like high ECD, and the difficulties to pump cement at the proper rate. So that's the same thing. It is common, I could see, in different area, different operator, and even different types of wells. When we are dealing with this issue, cement slurry design is really important, and we're trying to bring the downhole pressure down. So how we are bringing it down, let's discuss in the next slides. Here is just the design for this well, just intermediate and production all the way down to around 29,000 feet. TVD was around 10,000. As you see, around like 19,000 feet lateral section. And 4.5 in 6 3/4 open hole. That was the big challenge, to keep the pumping rate as high as possible. For this specific design, they had cemented sleeves, and the pumping rate couldn't be really less than 4 barrel a minute. That was dictated by cemented sleeves company. They wanted to have like a momentum to keep the dart running through that restricted area. At the same time, they had like high formation pressure, so heavy mud in the hole. You need to follow the rheological hierarchy and density hierarchy, and to see cement density cannot be less than like some value. So you have a restriction there. And pumping rate, you need to have high pumping rate, so the downhole pressure as a result will be high if you don't do anything. Gas migration was another like challenge there. So cement cannot be like simply designed with low rheology and just sacrificing the gas control property of the cement. Loss of circulation, additional like challenge there. So if you just, as I said, reducing the rheology, you're going to end up like with like higher volume of the cement getting lost through the formation. And on the top of that, pumpers limitation. You don't have like many companies. There is a limitation on the pumpers, like horsepower. You cannot just have a cement with any density or rheology and trying to keep the pumping rate as high as possible. Most of the cases, you need to have double like pumpers on location and pump the displacement simultaneously. That's going to be additional cost and complexity, and logistics going to be more complicated. So let's see here, and we are talking about ECD, or equivalent circulating density. That is representative of downhole pressure or any like formation pressure you're concerned about. In general, we need to bring the ECD down, but the main question is how you want to bring the ECD down. Here, I try to just get assistance from the Darcy-Weisbach equation to make the scenario slightly simple. If you're looking at the downhole pressure or pressure loss, or like pressure, like fluid resistance, whatever you wanted to call it, it is a function of the friction pressure, friction factor, a link of the, let's say, well or annulus, and cross section of the annulus. You can call it like hydraulic diameter, wet diameter, in different like topics, they're calling it differently. Density of the fluid and velocity. You see the velocity has the highest like factor here, and that's why on location you see if they have losses, they bring the rate down. That means reducing the velocity, and that has huge impact on the downhole pressure and controlling losses. But the fact is, if looking at this equation, what we can change here if we wanted to bring the downhole pressure down. Link and diameter, we cannot touch that. That is part of the well design. Velocity, yes, we can bring the velocity down, but for this specific case, that was a restriction to keep the dart running. That's why we didn't want to touch the velocity. But in general, bringing the pumping rate down is not really ideal for any cementing job, because you're just have more tendency to end up with channeling and intermixing of the cement, spacer, and mud. And you're losing the energy of the fluid to clean the hole. And then at the end of the day, you're going to have like poor cement bond and cement integrity. So velocity, it's better to not touch it. But if you have to, if you don't have time running simulation, first thing we do is just changing the pumping rate to a lower rate to reduce the velocity and reducing the downhole pressure. But let's be focused here on the friction factor and density. So talking about density, you can reduce the density, but in most of the cases you have like limitation with density as well. If you have heavy mud in the hole to control the well, if you have well instability and high formation pressure, there is restriction there. And in general, lower the density, how you're bringing density down, you're adding more water. And if you don't have like glass bead or just expensive design, adding water, it's like just sacrificing the amount of the cementitious material in the blend. So now you have like a lower compressive strength, and you're making it like more sensitive to mud contamination. So now let's put the density aside. We try to just keep the density as high as possible. So let's just jump to the remained function here. The remain factor is friction factor. Friction factor is like viscosity, plastic viscosity, and yield point, and or apparent viscosity. That has huge impact on the friction factor. So on this project, we try to reduce the viscosity, but at the same time, we needed to maintain the cement property, including the free fluid and fluid loss and sedimentation, and all of them are getting impacted by reducing the viscosity. So how you can just maintain the cement property just by holding the yield point high, and when cement goes to static, is not losing the property and ending up with free water, fluid loss, and sedimentation. But at the same time, you could bring the plastic viscosity down. When cement is in motion, you have some assistance from the motion and increasing the ECD with pumping cement. Once cement goes to static at the end of the job, mainly, cement has a high yield point to hold the particles in place and hold the property of the cement. These are the slurry design requirements. This is pretty much is common for all the production jobs. 0 free fluid for lateral section, that is for short, and 500 psi compressive strength within 48 hours. This is the minimum requirement, and silica flour that is required to prevent the thermal retrogression over time for high temperature design. And fluid loss needs to be less than 100 cc per 30 minutes. That's the unit they are using for measuring the fluid loss. And sedimentation is the biggest part of this. That is more, to me, is more and the most reliable variable you can look at when you have any concern with losing the property of a cement. Rheology needs to be controlled, and density, both of them, to maintain the rheological hierarchy, especially when you have like heavy mud in the hole. That was another restriction for this design. And transition time. Raf mentioned that one just briefly. Transition time is getting impacted by different variable, and one of them is density. How is the hydrostatic of the cement? It's coming from a column of the cement and also from the density of cement. So transition time can also be impacted by reducing the density of cement, at the same time reducing the rheology. Thixotropic property, that's the one when I try to just make this one simple. Thixotropic property means when you're pumping a cement or any fluid, when it's in motion, you're losing the viscosity. If it goes to static or lower rate, you see higher viscosity. That was another criteria here. Here I listed the conventional lead tail design. That was the original design. And at the first step, we changed the tail, which had higher the viscosity. We changed the tail to have different density. At the first step, it reduced the density from 14.6 to 13.75. Sorry, it's just weird density because I converted that one from SI unit to imperial. But 13.5 was equivalent density. Then in next step, we could see room there. Okay, we could change the density back to the original one, 14.6. In some cases, when they had higher formation pressure and more requirement for backside or maintaining backside pressure, especially at the end of the job, we could see room to increase the density and improving the design. And with all those changes, comparing the viscosity of the new design versus old design is less than half, if looking at this one. And on the actual job, I don't want to go through all these numbers here, but the main one, I just changed it to red here, is 264 was just I think I could see this one. Most of the design within range of the 14.5 or 14.6, it is common plastic viscosity. We change it to around 11-15, and with that change, you could reduce the downhole pressure drastically, and also we could change the cement density to even higher density and still having almost same ECD as original one. That was just for a special application when they had like high formation pressure. Simulation was used at its first step and see what's the impact of the changing density as changing the rheology. You could see on the top, it is original one. We had to bring the rate down to 2.5 and finally to 1.6 for past 75 and 94 barrels. But with the new design, we could keep the pumping rate like 6.3 and finally 4.4, and was not less than 4 barrel a minute for entire job. One thing I mentioned about the density, why ideally we don't want to reduce the density, it is more sensitive to mud contamination. And here is just some proof. And 13.3 with 10% mud contamination, you see that the compressive string, especially here, is changing to 702, almost half. And the original compressive string in 48 hours is 1440. But if you change it to heavier density, that is, it is just in theory makes sense. We wanted to just prove it on the actual testing data. 2441 was the original one. Even by 10% contamination, it still is higher than original or pure slurry designed with 13.3. So the fact here is just having the higher density always is ideal to keep the cement property, and especially talking about the compressive string and cement integrity over time. Actual job, this is just one example of the I think it was 28,000 feet executed, and you see the pumping rate here. Majority of them was 5 or over 5, and the minimum was 4 barrel a minute. As conclusion here, design for any changes, design needs to meet all the requirements dictated by client or by board or any regulation. And we use here laboratory analysis and simulation software to evaluate before introducing this fund on the actual job. And this change could help the client to extend the lateral with no concern with cementing, and running the dart through the cemented sleeves. That was some cases they had cemented the sleeves. And mud removal, displacement efficiencies on the 3D simulation was showing like, and this is just the general comment here, if you pump the cement faster or spacer faster, you have better displacement efficiencies or less mud contamination or channeling, different terms is used. And minimizing the risk of gas migration, and that is by reducing or maintaining the transition time less than 45 minutes, and from 100 to 500, and also 30 is ideal, but 45 is a minimum requirement. You have any concern? And also with those changes, we could eliminate the lead entirely and use just single cement design, because ECD was not really concerned there. And we could have just one cement design to be used for long lateral one. And that helped with logistics. First of all, it's safer. And you could have the higher density in the vertical section, ending up with higher hydrostatic and less requirement for backside pressure when you have concern with the high formation pressure. And here's some data. Over 100 jobs have been executed. That the range of temperature was 230 to 250 Fahrenheit. And what's the application here? I know we are talking about geothermal. Just a general comment here, just using or picking the proper additives to customize the design to get the target like plastic viscosity and yield point. That was the main target of the project. And I could see recently on one of the geothermal, they had concern with losses. At the same time, they didn't want to have any loss circulation material to close the like pores. Probably holding cement or keeping the thixotropic property of the cement that prevents losses. At the same time, you're not adding like additional pressure downhole by reducing the apparent viscosity. That helps with loss of circulation. And that could be one of the applications for any types of cementing job. And how you could just validate the improvement. That for this project, I was talking about like displacement efficiency is getting better. Simulation is saying something, but actual job, it could be different because of tons of variables there. Just like, for example, if you don't have good centralization, the one Raf just covered in the previous session. We were monitoring the return. You could see more return of spacer or cement if you design the cement back to surface when you're pumping it at lower rate. By adding the rate to like faster or higher pumping rate or higher velocity, you could see the improvement. You see, get the expected volume of cement or spacer back to surface. That was the best indication. That's it. Thank you for your time. If you have any question, I will be more than glad to answer.
Thank you, Afson.
Yeah, good presentation. Just wanted to make a comment. Of course, when you're talking about long horizontals, free fluid is also a key factor. I'm sure you tested that. But if you can go to slide number 6, I had a question about, or was wondering, let's see. I think you showed thickening times longer than the time to 500 PSI. I was wondering if you can comment on that.
Yeah, that's a common question we are getting from different clients. When you're talking about thickening time, the way we are running the test and that needs to be run at that way, cement is in motion. And I wouldn't be surprised to see, in general, yes, longer thickening time for a specific design is going to end up with longer time to 500 PSI. But doesn't mean necessarily those time needs to be less or more. But if you're talking about the same design, you're extending the thickening time, you should see longer time to 500 PSI. But the testing is done at a different way. Compressive string test or UCA, they're using UCA ultrasonic when cement is in a static. And I could see some of the design, if you have any types of salt, like sodium metasilicate is one of them, that you have extended thickening time, but at the same time, starting compressive string development is going to be shorter and faster compressive string development to 500 PSI. So in general, you shouldn't really connect both together and compare them because they are different testing and a different way of a different mechanism, I would say, of the testing.
And are they preconditioning in a consistometer before putting it in the
Yes.
UCA?
Absolutely. Yeah.
Okay. Okay. So are you including that preconditioning time?
For a static, no. For like UCA, normally we are conditioning it within the job placement time and temperature. Try to use simulation as this is the trend of the conditioning, like in HPHT, high pressure, high temperature. Try to just approach the actual job condition as much as possible, and then just passing it to UCA machine to run compressive stress.
Correct. My question is, are you adding on that conditioning time to the time to 500 number?
No.
Okay.
No.
Okay.
Yeah, that is started when you bump the plug, and that just started from that point in actual job. And then testing, once you put the cement, condition the cement, time doesn't really start till then. And then when you pass it to the UCA machine, the time is started from that point. I hope I answered the question.
Sick.
Thanks, Bill. Just a quick comment and question. Have you ever considered running rheologies at bottom hole circulating in these higher temperatures? I say that I was involved in a well where we couldn't place the cement theoretically when we used surface rheologies, and when we got downhole rheologies, it all became possible. It's significantly different.
That's a really good comment.
It's
Normally
almost
we are
never
running,
done, but I would suggest it.
No, we are doing it, and that is different machine. Is not really the conventional fan machine. That is the Chandler is the high temperature, high pressure rheometer. But on this project, what we could see, monitoring the actual job data, like pumping pressure, and trying to match those data with what ISIM or the simulation we are using to see how close is that one, and then check the reliability of the data. But in general, we are running it at 3 different temperatures, not at the actual bottom hole circulation temperature, but we have done it, and we are doing it for some of the cases. ISIM extrapolation on the temperature and rheology behavior. It is close enough. It is giving us even worst case scenario. It is close enough to actual, unless you have like some weird design and weird additive that behaves like weirdly at high temperature and just turn the cement to thicker. I couldn't see that one in any design, but that I think is the fair comment. Rheology needs to be done at the proper bottom hole circulation temperature. But for the as far as it goes with downhole pressure prediction, as extrapolation, it is giving us a good enough estimation, if it's not really worst case scenario.
Okay, nothing else? Thank you very much again, Ashwin.
You're welcome.
And it's break time. We start again at 10 o'clock.
Couldn't be here. He had a family.
Okay, we could take a little break, meet back here right at 10 because we want to get moving on so we can move with the compressed agenda as best we could. So 10 or a little bit before would be great. Thanks. right, we'll see you afterwards.
Yeah, I'll be back.
Okay.
Our Geothermal Technologies Office has been investing in developing and deploying geothermal for decades. And we've asked Congress for $57 million more for this program in the upcoming year.
This is the Allen S. King coal-fired power station. It produces 600 megawatts of steady, reliable baseload power. Shutting down this power station is the right thing to do, as we've got to stop burning fossil fuels and save our Earth. The problem is, we can't replace this power with just wind and solar. In California, the Public Utilities Commission has finally and formally recognized this problem and has now called for 1,100 megawatts of firm and renewable 24/7 electricity generation by 2026. That's geothermal energy.
We're learning from both successes at the state level, like last year's California Public Utilities Commission procurement decision that geothermal rising helped to boost. And we're learning from our international work, obviously, like Europe's progress on district heating systems. In April, we announced $15 million for geothermal research projects in West Virginia as part of our investments in job creation and economic opportunities in the hard-hit coal and power plant communities area.
WVU Morgantown campus has been identified as a priority location for deep dive-infused geothermal project. Therefore, to perform a geothermal resource quantification and risk assessment, an exploratory well will be drilled to a depth of 15,000 feet, along with a full logging and coring program. We'll be using state-of-the-art drilling technologies for this exploratory well. The project will have implications beyond West Virginia University campus. It will provide data for geothermal resources for other potential sites in the Middle Appalachian Basin that has similar geology and demonstrate geothermal energy is a national resource but not limited to Western states.
Department of Energy sees geothermal as a crucial tool to help us tackle the climate crisis, to deliver 40% of the benefits of clean energy to disadvantaged communities, and to build a skilled, diverse energy workforce.
The newly formed Diversity, Equity, and Inclusion Task Force has been very busy since we formed 7 months ago. Our first goal was to create a DEI statement that shows Geothermal Rising's commitment to improving diversity, equity, and inclusion across the geothermal community. Geothermal Rising is committed to improving diversity, equity, and inclusion to provide a brighter future for Earth and all its inhabitants. Our organization and community embrace and celebrate our members' differences. It is a responsibility of Geothermal Rising to encourage and promote diversity, equity, and inclusion. As a global geothermal nonprofit organization, we are committed to connecting the geothermal community. There is more work to be done, and as we expand across markets and internationally, Geothermal Rising will continue to seek equitable improvement to elevate the geothermal community.
The infrastructure investments that are in President Biden's Build Back Better agenda are going to turbocharge geothermal energy in America. We're talking about the biggest investment in clean energy and transmission in history. So my message to you is this: when it comes to geothermal, America is open for business. We are so ready to partner with you to get this done. We are grateful for your tireless work to elevate this important, clean, and reliable energy source. And we're grateful for your willingness to train the next generation of geothermal professionals. And we are excited to secure policy wins all across the country. So thank you so much for inviting me to participate. I hope you have a fantastic conference. Our Geothermal Technologies Office has been investing in developing and deploying geothermal for decades. And we've asked Congress for $57 million more for this program in the upcoming year.
This is the Allen S. King coal-fired power station. It produces 600 megawatts of steady, reliable baseload power. Shutting down this power station is the right thing to do, as we've got to stop burning fossil fuels and save our Earth. The problem is, we can't replace this power with just wind and solar. In California, the Public Utilities Commission has finally and formally recognized this problem and has now called for 1,100 megawatts of firm and renewable 24/7 electricity generation by 2026. That's geothermal energy.
We're learning from both successes at the state level, like last year's California Public Utilities Commission procurement decision that Geothermal Rising helped to boost. And we're learning from our international work, obviously, like Europe's progress on district heating systems. In April, we announced $15 million for geothermal research projects in West Virginia as part of our investments in job creation and economic opportunities in the hard-hit coal and power plant communities area.
WVU Morgantown campus has been identified as a priority location for deep diffuse geothermal project. Therefore, to perform a geothermal resource quantification and risk assessment, an exploratory well will be drilled to a depth of 15,000 feet, along with a full logging and coring program. We'll be using state-of-the-art drilling technologies for this exploratory well. The project will have implications beyond West Virginia University campus. It will provide data for geothermal resources for other potential sites in the Middle Appalachian Basin that has similar geology and demonstrate geothermal energy is a national resource but not limited to Western states.
Department of Energy sees geothermal as a crucial tool to help us tackle the climate crisis, to deliver 40% of the benefits of clean energy to disadvantaged communities, and to build a skilled, diverse energy workforce.
The newly formed Diversity, Equity, and Inclusion Task Force has been very busy since we formed 7 months ago. Our first goal was to create a DEI statement that shows Geothermal Rising's commitment to improving diversity, equity, and inclusion across the geothermal community. Geothermal Rising is committed to improving diversity, equity, and inclusion to provide a brighter future for Earth and all its inhabitants. Our organization and community embrace and celebrate our members' differences. It is a responsibility of Geothermal Rising to encourage and promote diversity, equity, and inclusion. As a global geothermal nonprofit organization, we are committed to connecting the geothermal community. There is more work to be done, and as we expand across markets and internationally, Geothermal Rising will continue to seek equitable improvement to elevate the geothermal community.
The infrastructure investments that are in President Biden's Build Back Better agenda are going to turbocharge geothermal energy in America. We're talking about the biggest investment in clean energy and transmission in history. So my message to you is this: when it comes to geothermal, America is open for business. We are so ready to partner with you to get this done. We are grateful for your tireless work to elevate this important, clean, and reliable energy source. And we're grateful for your willingness to train the next generation of geothermal professionals. And we are excited to secure policy wins all across the country. So thank you so much for inviting me to participate. I hope you have a fantastic conference. Our Geothermal Technologies Office has been investing in developing and deploying geothermal for decades. And we've asked Congress for $57 million more for this program in the upcoming year.
This is the Alan S. King coal-fired power station. It produces 600 megawatts of steady, reliable baseload power. Shutting down this power station is the right thing to do, as we've got to stop burning fossil fuels and save our Earth. The problem is, we can't replace this power with just wind and solar. In California, the Public Utilities Commission has finally and formally recognized this problem and has now called for 1,100 megawatts of firm and renewable 24/7 electricity generation by 2026. That's geothermal energy.
We're learning from both successes at the state level, like last year's California Public Utilities Commission procurement decision that Geothermal Rising helped to boost. And we're learning from our international work, obviously, like Europe's progress on district heating systems. In April, we announced $15 million for geothermal research projects in West Virginia as part of our investments in job creation and economic opportunities in the hard-hit coal and power plant communities area.
WVU Morgantown campus has been identified as a priority location for deep dive-infused geothermal project. Therefore, to perform a geothermal resource quantification and risk assessment, an exploratory well will be drilled to a depth of 15,000 feet, along with a full logging and coring program. We'll be using state-of-the-art drilling technologies for this exploratory well. The project will have implications beyond West Virginia University campus. It will provide data for geothermal resources for other potential sites in the Middle Appalachian Basin that has similar geology and demonstrate geothermal energy is a national resource but not limited to Western states.
Department of Energy sees geothermal as a crucial tool to help us tackle the climate crisis, to deliver 40% of the benefits of clean energy to disadvantaged communities, and to build a skilled, diverse energy workforce.
The newly formed Diversity, Equity, and Inclusion Task Force has been very busy since we formed 7 months ago. Our first goal was to create a DEI statement that shows Geothermal Rising's commitment to improving diversity, equity, and inclusion across the geothermal community. Geothermal Rising is committed to improving diversity, equity, and inclusion to provide a brighter future for Earth and all its inhabitants. Our organization and community embrace and celebrate our members' differences. It is a responsibility of Geothermal Rising to encourage and promote diversity, equity, and inclusion. As a global geothermal nonprofit organization, we are committed to connecting the geothermal community. There is more work to be done, and as we expand across markets and internationally, Geothermal Rising will continue to seek equitable improvement to elevate the geothermal community.
The infrastructure investments that are in President Biden's Build Back Better agenda are going to turbocharge geothermal energy in America. We're talking about the biggest investment in clean energy and transmission in history. So my message to you is this: when it comes to geothermal, America is open for business. We are so ready to partner with you to get this done. We are grateful for your tireless work to elevate this important, clean, and reliable energy source. And we're grateful for your willingness to train the next generation of geothermal professionals. And we are excited to secure policy wins all across the country. So thank you so much for inviting me to participate. I hope you have a fantastic conference. Our Geothermal Technologies Office has been investing in developing and deploying geothermal for decades. And we've asked Congress for $57 million more for this program in the upcoming year.
This is the Allen S. King coal-fired power station. It produces 600 megawatts of steady, reliable baseload power. Shutting down this power station is the right thing to do, as we've got to stop burning fossil fuels and save our Earth. The problem is, we can't replace this power with just wind and solar. In California, the Public Utilities Commission has finally and formally recognized this problem and has now called for 1,100 megawatts of firm and renewable 24/7 electricity generation by 2026. That's geothermal energy.
We're learning from both successes at the state level, like last year's California Public Utilities Commission procurement decision that Geothermal Rising helped to boost. And we're learning from our international work, obviously, like Europe's progress on district heating systems. In April, we announced $15 million for geothermal research projects in West Virginia as part of our investments in job creation and economic opportunities in the hard-hit coal and power plant communities area.
WVU Morgantown campus has been identified as a priority location for deep diffuse geothermal project. Therefore, to perform a geothermal resource quantification and risk assessment, an exploratory well will be drilled to a depth of 15,000 feet, along with a full logging and coring program. We'll be using state-of-the-art drilling technologies for this exploratory well. The project will have implications beyond West Virginia University campus. It will provide data for geothermal resources for other potential sites in the Middle Appalachian Basin that has similar geology and demonstrate geothermal energy is a national resource, but not limited to Western states.
Department of Energy sees geothermal as a crucial tool to help us tackle the climate crisis, to deliver 40% of the benefits of clean energy to disadvantaged communities, and to build a skilled, diverse energy workforce.
The newly formed Diversity, Equity, and Inclusion Task Force has been very busy since we formed 7 months ago. Our first goal was to create a DEI statement that shows Geothermal Rising's commitment to improving diversity, equity, and inclusion across the geothermal community. Geothermal Rising is committed to improving diversity, equity, and inclusion to provide a brighter future for Earth and all its inhabitants. Our organization and community embrace and celebrate our members' differences. It is a responsibility of Geothermal Rising to encourage and promote diversity, equity, and inclusion. As a global geothermal nonprofit organization, we are committed to connecting the geothermal community. There is more work to be done, and as we expand across markets and internationally, Geothermal Rising will continue to seek equitable improvement to elevate the geothermal community.
The infrastructure investments that are in President Biden's Build Back Better agenda are going to turbocharge geothermal energy in America. We're talking about the biggest investment in clean energy and transmission in history. So my message to you is this: when it comes to geothermal, America is open for business. We are so ready to partner with you to get this done. We are grateful for your tireless work to elevate this important, clean, and reliable energy source. And we're grateful for your willingness to train the next generation of geothermal professionals. And we are excited to secure policy wins all across the country. So thank you so much for inviting me to participate. I hope you have a fantastic conference. Our Geothermal Technologies Office has been investing in developing and deploying geothermal for decades. And we've asked Congress for $57 million more for this program in the upcoming year.
This is the Alan S. King coal-fired power station. It produces 600 megawatts of steady, reliable baseload power. Shutting down this power station is the right thing to do, as we've got to stop burning fossil fuels and save our Earth. The problem is, we can't replace this power with just wind and solar. In California, the Public Utilities Commission has finally and formally recognized this problem and has now called for 1,100 megawatts of firm and renewable 24/7 electricity generation by 2026. That's geothermal energy.
We're learning from both successes at the state level, like last year's California Public Utilities Commission procurement decision that Geothermal Rising helped to boost. And we're learning from our international work, obviously, like Europe's progress on district heating systems. In April, we announced $15 million for geothermal research projects in West Virginia as part of our investments in job creation and economic opportunities in the hard-hit coal and power plant communities area.
WVU Morgantown campus has been identified as a priority location for deep dive-infused geothermal project. Therefore, to perform a geothermal resource quantification and risk assessment, an exploratory well will be drilled at a depth of 15,000 feet, along with a full logging and coring program. We'll be using state-of-the-art drilling technologies for this exploratory well. The project will have implications beyond West Virginia University campus. It will provide data for geothermal resources for other potential sites in the Middle Appalachian
Okay, everybody.
Basin that has similar.
We're going to try to start just a little bit early. We're still trying to compress everything so we can do the final today, the final panel today.
Sees geothermal as
everybody
a
take a
crucial
seat
tool to help us tackle the climate crisis, to deliver 40% of the benefits
Hello.
of clean energy to disadvantaged communities,
listens to
and
the
to build
chairman.
a skilled, diverse energy workforce.
The newly formed Diversity, Equity, and Inclusion Task Force has been very busy since we formed 7 months ago. Our first goal was to
Okay.
create a DEI statement that shows
We're getting
geothermal
ready to
rising
start the next session. But before we start the next session, I want to remind everybody that we asked you to write down a couple of things on a piece of paper. One is, what do you think about this workshop? What do you think we need to do to make this to get our point across about cementing?
commitment
But
to
also, I'd
improve
like everybody to write down what you think another workshop should be, the next workshop should be. I've heard suggestions on case and design, case and failure, and a little bit extension of the cementing side, because we're not going to hit all of it today, I'm sure. So everybody, please take a minute just to write down a couple of little things. What do you think the next workshop could be, and what do you think we need to do to make this thing a home run? It's cementing a household word, I guess. With that, I'd like to turn over to our chairman for the next session, Maleva, and Mark. I don't know who's going first, but give us a little brief, and we're ready to get started. Thank you.
Well, happy Friday, everyone. I'm Mark Brennan, and we have a slight change in the program here. Cody had a family emergency and cannot make the speech today, so Maleva is his professor, so she knows the subject matter very well, and she'll be making the presentation for him today. And co-moderating today will be Harpita, who spoke yesterday. And we'll have our clock on to make sure that Maleva doesn't go over her time, and we'll keep things moving along.
Gave a secret that all college professors like to talk a lot. So Mark said, okay, I'll keep you in check.
So without any further ado, we'll get started.
Okay. All right. Thank you. So what I will do is I will cover Cody's research, and then at the end I'll do like a slide or two on what I was supposed to, what another student was supposed to present this afternoon, so that we have some time for discussion that I would like to start this afternoon. So a little bit about who I am. I'm currently working at the Oklahoma State University as a faculty, and I'm a geologist and material scientist by training. And my involvement with wellbore cement really started when I was a postdoc, and we looked at wellbore integrity in relation to CO2 storage. The next one on wellbore integrity was a project funded by the DOE on geothermal cements, and we looked at various fibers and other additives. This was for depleted oil and gas reservoirs in Louisiana and how the thermal energy or heat harvesting could be done there. After that, there was another cement-related project where Shell observed something in the field, and I really, as someone who is involved in science that gets applied, I really like to hear from the field, from people who see the problems and observe them, and then tackle those issues in a lab. So that project was on how we can mitigate microannular gas flow. And so they observed that during expandable tubular procedures, they got much better cement bond logs. So we engaged in that research for about 4 years, and I think it's an ultimate dream of a researcher to see your research actually be implemented in the field. So Shell is using now this technology. What happens to cement from a hard rock-like type of material, when you compress it in confinement, it turns into toothpaste type of material and then starts secondary hydration. So that was another time where I had to change my mind about what I thought I knew about cement. I realized I didn't really know everything. So the last one that is ongoing project is developing P&A type of materials for the Gulf of Mexico, sponsored by the National Academy of Science Gulf Research Program. And during the workshop on that, the SP actually forum is when I met Daniel Bohr, and that has been a very useful connection. I think I would like to say that he means it when he says, ask for help and we're here to help. He has been helping a lot. So in this particular research for Cody, it was Daniel who brought this idea that we should investigate graphene. So why graphene? I'll get into that in a minute. But I do want to point out that this research also engaged my collaborators from Pittsburgh. Yunsheng Lu, who will be presenting later today also, is a PhD student, and his advisor, Andrew Bunger. And we did the CT scanning at NETL labs, and the scientist there is Dustin Crandall. Acknowledgement, I already acknowledged the NASM GRP and my collaborators. I'm the PI, but I have partners from LSU, Pitt, UTA, and SINTEF Norway. Daniel and Paul Basant were really instrumental in providing inspiration for graphene research, and then people at the OSU. So this is, I think, seen probably 5 times already yesterday, but I'm going to go back to basics. Why cement fails and how, in terms of mechanical failures. I think this schematic that I borrowed from Susan's and Daniel's presentation shows it really well. But I added these little blue kind of glitchy pathways of where the fluid comes in. So something that might start mechanically actually later turns out into, especially in geothermal conditions, into chemical attack and dissolution and precipitation and all sorts of durability issues. So we know we want from cement to provide mechanical stability, give us chemical protection for casing and holds that casing in place. We also want zonal isolation. To do these things, we would need a material that is both strong and ductile, that is impermeable, that is geocompatible. At the moment, when we look at Portland cement, its pH is 13 to 14, and we place it into the subsurface where really nothing where we're placing this has that kind of pH. So nature equilibrates everything. So 13, 14 does not really, cannot definitely stay there for a very long time. It has to get to some sort of equilibrium with the surrounding chemistry. And the durability, I think static conditions are okay, but if we really want good data, we need to really engage into dynamic conditions, to have a fluid flow, to have temperatures and pressures cycling as they would in a field. And we need to do that in a lab. So how can we do some of these things? I think we need to shift composition of Portland cement, and you can rename it and call it something else. I honestly don't care about the names, but it's the material that and its properties and function that are important. So I think calcium is probably not the good component in the OPC. So changing that towards silicium, aluminum, magnesium would be better. Shifting pH to a less alkaline environment, shifting microporosity to nanoporosity. We know that when we look at natural barriers, the effective barriers are those that have primarily nanoporosity. And then the last one, I've been kind of dreaming about this. How can we have a material that is function-based? So it's almost like, you want to make, okay, I love cakes. So you go to a shop and you want to make a chocolate cake, you know exactly what ingredients you need to buy. So the same here, like if you're going to have a cementing in a CO2-rich formation, you have to have something in that cement that is going to address the CO2 attack. If you have H2S equally, then you have to, I don't think we can have one size fits all. I think that's really setting us up for failure. So being a geologist, I like looking at how nature does it. And so shale is probably one of the best Earth's barriers that we know. And so when you look at this, I think originally this was made by Halliburton, but I think it was published now in so many different papers. I just like the simplicity of this chart. So you look at, okay, what does it take to make a good barrier? You have inorganic and organic materials. You have pores in both of these components. And then when you look at the inorganics, you have nanomaterials like clays, and then some strong materials like quartz and calcite, feldspars, there are a bunch of others. Down in, at the bottom, in this triangle, this is a kind of a very simple division of when shales move from cap rocks and good barriers into what we call now fracking shales. So if you stay close to that corner where the clays are on the left, you're going to have a very ductile material that is really hard to break. And so I'm thinking that's where we need to be. So back to basics with OPC hydration. At the very start, this is a publication from Lausanne. Professor Karen Scrivener is heading that team, and they've done enormous amount of research. They're sponsored by Lafarge, powerhouse really when it comes to cement and cement products. So when you look at the evolution of cement, you can see that densification is really when you start to lose the properties such as ductility, because they have figured out that the type of minerals that develop actually can be translated into ductility or brittleness. So if I want to, from this third chart, if I want to try and not go completely into that last picture, number 4, where everything becomes very dense and more brittle, I need to do something and interfere with some nanoparticles so that I actually provide different template for crystal growth. And I think that is where the graphene kind of really fitted nicely. So what is graphene? I mean, that's a kind of an easy Google search, but it's really very thin and currently strongest material that we know of, although it comes from a fairly weak material called graphite. So why it's so strong is simply because you take it to the nano thickness. And so we got this material from a contact that Daniel provided for us, Paul Bassant. These particular graphene nanoplatelets are actually products of bio waste, which is another good thing. We're actually doing something with waste materials. So what did we do? We tried to basically see how would this work for a plugging and abandonment project in the Gulf of Mexico. So we made 16.4 density cement slurry, following API class H, and we played with 3 different concentrations. The first one, 0.008, is really what is reported in cement and concrete research as a good number, but we thought, let's push it a little bit further and see what happens. We cured our samples at 90 C. For 28 days. Those are temperatures that are kind of relevant to the Gulf of Mexico. We did not cure these cements at pressure. That's the only downside that I see in our approach. That was a limitation we had in our lab, and I think it's important to be open about that and report it. So the testing, thorough material characterization and mechanical characterization, because that was really the important thing for these plugs to survive in the Gulf of Mexico, as some of these reservoirs go through repressurization. And the new demand from the both federal and the state regulations in the US is kind of picking up of what is already the case in Europe for the North Sea, both Norwegian and the UK government really talking about 10,000 years durability of these plugs. So here is how that graphene looks in the cement after cement is hydrated for 28 days. We always compare the neat, which is just class H with some bentonite, nothing really else, and then the graphene. So if you look at the bottom right, comparing neat to graphene enhanced cement, there is really not a global difference in terms of hydration products. You still see a few unhydrated clinker minerals appears very similar. On the top left, you see how the pores look like in the GNP enhanced cement. You can see these over here, these very, very thin platelets of graphene fitting really into that pore space. So graphene is kind of interesting. It's hydrophobic. So it goes into this pore space. It doesn't really attract lots of other water into it, but I think these thin platelets, they do provide some reinforcement. That was our hypothesis, but we really needed to prove it. So we started kind of looking for more evidence of this. So it's not like, it's always dangerous in a lab. Like you know what you want to see, and sometimes you kind of you make yourself see what you want to see. And then so looking at this numerous samples, fractured, polished, it was clearly there. So the next thing was, okay, let's look at the porosity. We did both helium porosimetry for neat and for graphene. There is obviously some error involved with these measurements, but 0.008 was kind of okay. The MIP also didn't really show any major difference in terms of how the pore throats or pore sizes were. Again, I was okay with this because initially I was disappointed, thinking, but where is this graphene? You know, I want to see some evidence on its impact on porosity. But it later kind of became clear that the graphene nanoplatelets do not actually reduce the volume of the pore. They just sit there as a very thin plates and provide reinforcement. We did some indentation to look at how material behaves at the micro scale so that we can relate that to single phases from the previous images that I've shown. And so the downside of indentation is that you're really not having sample in confinement. So the elastic modulus and hardness that we obtain from these measurements are more as an indicator, like, is this substantially different or not? But that is not the kind of test that I would rely completely in terms of is graphene qualified to be used in the field? That test is coming later. But you can see that 0.08 did actually contribute in reducing the Young's modulus. Now, this is what I call like the most relevant test to industry. So we have samples, we have our cores in confinement, and then we do this triaxial testing. This was done at Pittsburgh University. And the man who did all the testing sits right there, Yunxing Liu. He's a PhD student. And so we did actually, as you can see, he plotted it here nicely. Your neat cement is this orange yellow, I guess. It's not really OSU color, right? It's too yellow. And then the top three lines are different GMP percentages. In this one, it turns out that the 0.05 actually performed better than the 0.08. And so my take on this is it is really important to apply different methodologies when you are validating material and qualifying it for any application in the field, because this data is in a slight disagreement with the nano indentation, which was not done in confinement. So where from there? Okay, we have these samples, they fractured in triaxial test. We pushed them to the limit, and now we wanted to see how do these fractures look? Does the graphene really make any difference or not? So you can see NEAT on the left and the graphene enhanced cement on the right. So the volume of the fractures and their connectivity is really disrupted by graphene. So I would say thumbs up on this one. But there is still much more work really to be done. So if we then, everything that we obtain in a lab, we need to make sense of what we see with what other researchers have done and what they've reported. So there is quite a bit of research in concrete where they used the graphene type of materials. So we looked at that. And for our application, because everything is still very fine, it's just cement paste effectively, it seems that graphene really sits in those pores and microfractures. It is also because it does not attract water, there is no water film that forms on its surface. So, it's a really good substrate for the crystal growth. And I think it does probably, this is a study that we need to conduct on the pure phases using only C3S and graphene to see how actually graphene impacts CSH morphology. And then the other thing that we did observe in some preliminary study where we put graphene into different solutions that it actually does attract calcium. So maybe that's how it impacts CSH hydration or formation. So what is the potential mechanism of why we see those good results in the triaxial data that I just reported earlier? I was looking at some work that was done on the shape of CSH and how that translates to Young's modulus. But then the other one is, in some instances, these graphene nanoplatelets, they're so thin and we don't really effectively disperse them completely. So they always come in maybe 2, 3 stacked together. And so what they do, I believe, they kind of slide as deck of cards as they are subjected to load. And I think instead of having abrupt fracture and brittle behavior, they kind of extend that time and the material can survive a little bit longer. In terms of cement hydration, crystal morphology, as I said, I think there is a little bit of evidence in this video. So what is this? This is, you take a small piece of cement, you put it in a focused ion beam microscope, and then you keep slicing through it. And these are, as you can see, we're looking at the scale bar is 10 microns. So this whole box is something like maybe 12 by 12 by 12 microns cube. And that's the scale that you need to be in if you want to look at the particles that are like that small and you want to look at the calcium silicate hydrates because they're really at that sub-micron scale. So we did kind of, I'm going to just play this one more time. So if you look at these elongated kind of black shapes, those are like graphene nanoplatelets. And I think, although this is still just, I would call it still a little bit preliminary, this FIB SEM is supporting our hypothesis that I showed earlier. How I'm doing with time? Okay, 15 minutes. So I'm going to, okay. So what are the major observations from this? We see the graphene reinforces cement pore walls and fractures, microfractures, I should say. It really doesn't, we don't see it in terms of major change on the CSH shape because that cannot be obtained from looking at cement. You really need to do that with graphene in C3S type of slurry. we saw the increase in the axial stress at 90 C, 2000 PSI confinement, and I believe in some cases, usually you went even above 9000 PSI, right? Okay. Addition of graphene did reduce brittleness, and then these nanoplatelets, as graphene nanoplates is still kind of, there is really no uniform standard when you're purchasing these materials. So they do have some impurities, and we don't know how those impurities might be impacting cement hydration. Where do we want to go from here? In addition to looking at graphene, we also looked at some zeolites and we looked at olivine. And I'm not going to steal the show because Yunxing is going to show olivine paper later today. But you can see the neat is this curve in red, and then the rest are all these other different additives. So where am I heading with this? I imagine that a new generation of wellbore cement is going to be, Daniel called it boutique cement. So you're going to go and select different ingredients that you need. So ferrite, for example, has this mesostructure. It takes some of that cement pore water. So if you add it in a right amount, up to 5%, it removes that excessive water that is needed for rheological pumping down of cement, but actually really increases and causes microporosity. So that could help maybe shift everything into nanoporosity range. Then later on, if you have a fracture and you need that extra aqueous chemistry to heal the fracture, the zeolite will release that water and you actually end up forming the bridging elements in the fractures. With olivine, it's all about its reactivity with CO2. And again, Yunxing will show that later today. But I believe that we need to be compatible with subsurface. In geothermal, that's even more important than in oil and gas, because you're in hard rock, you're in a high temperature, and you're in very aggressive geofluids type of environment. Here are the references. That's it. I'm done.
We have some time for a few questions.
Have you thought about looking at how the graphene affects the thermal conductivity of the cement?
Yeah, sorry, I forgot that. That is in our proposal to Geothermica with the group from Europe, with TNO and a few universities from Germany and partners here at LBNL. Sintev has done some work, and actually graphene really is good for that. Plus, it can actually be used in capacity of self-sensing. So you could use it for monitoring by simply using electric conductivity. And so those are the kind of, other good things about graphene. Thanks for reminding me.
Thanks for the presentation. Very interesting. Apologies if I missed it, but were there any studies or any notable features for the slurry properties that graphene imparts, whether on the mixability, rheology, or fluid loss, anything like that?
No. The only thing that is a problem, and I should really talk about this. So like, these were powders. So how do you use these materials in the field? Again, in consultation with Daniel, we thought this really needs to be formed into some kind of liquid. So you would apply it like that, add it to your, slurry before you add cement. That would also help dispersion, because I know that we didn't do the best job in dispersing this stuff. So we did have maybe sometimes a thicker deck of cards in some places than the other. And I think that requires improvement. But I believe that the role of academia and our fundamental research is to kind of identify some of these products, like just do the basic interrogation, and then probably with all the secret chemistry ingredients that you guys have at Schlumberger, Halliburton, elsewhere, I think you can tweak it to do the rest.
Thank you.
This is regarding porosity. To some extent, don't we want to have porosity in the system to prevent propagation of fractures?
So the pores themselves, in my understanding, are not preventing necessarily propagation of fractures. But what happens in these pores, the graphene is actually not changing the volume of the pore. So it really is like, if you look at this room, I think graphene stands like this posts, right? They're very thin layers, and they just kind of do crisscrossing across the pore space. The microporosity is the one that is really making material mechanically weaker, and it's obviously making it easier for any aqueous chemistry to invade it. But the nanoporosity will remain there because it's dictated by the packing of calcium silicate hydrate needles, and that's a good porosity. Did I answer? Okay.
So I had a question. So the micro indentation data, so since you said that it also varies a lot from the triaxial data, so can the reason be that when you are doing the micro indentation, you have to be sure where you're hitting it?
Yes.
Like whether it's the anhydride cement or it's like the C3S or it's the CSH. So was it like?
Yeah. So basically with the micro indentation, you're still hitting several grains. So you're averaging. If you go into nano indentation mode, then you can distinguish between CSH and other grains. And there wasn't really like a huge, it's not like the nano indentation didn't show improvement and reduction in Young's modulus. It just seemed to pick on different, it showed better results for 0.08% of graphene versus triaxial, which had better data for 0.05.
Any more questions?
Online?
Online, okay.
No?
No? You done?
I think that's it. You'll leave a very good job. Okay, our second module is going to be methods for improving cement performance and integrity in thermal wells. Simon, your monger.
Yes, I'm here. I'm just, I'm not.
He's
able to share
online.
my
He's
screen
online,
at the moment.
okay.
Sorry, it's just indicating I can't share my screen while somebody else is sharing.
Good morning, Simon. Good morning, Simon. Can you hear us?
Yes, I can hear you coming through. I'm not sure what the issue is.
Good morning. Well, we can hear you too. I think we're good
perfect.
to go.
Okay, I'll just, I have an issue here. It's just saying I'm not able to share my screen while the other participant is sharing.
Okay. Okay, how about now?
Yes, it looks like it's working. Can you guys see that?
There we
screen?
go. Yes, we have it
Perfect.
up.
Awesome. Yes, thank you very much for that introduction. As was said, I just want to talk about some methods for improving cement performance and integrity in thermal wells. And really kind of talk about some, the key questions and opportunities that I want to talk about is, what are the potential failure modes for cement? I think if we can understand, how cement is potentially failing downhole, then we're going to be able to, deliver better solutions. Obviously, there's already been a lot of talk about this, so I won't dwell too much on that. Certainly discuss what cement properties are important, how they're determined. Some of the strategies that we've kind of looked at for improving these properties, and how do you validate, the performance. And really kind of just try and share, in the interest of this being a workshop, kind of share some of the lessons that we've learned for some different ways for improving properties. And that, we've been able to learn from the proving ground, which is the Western Canadian Sedimentary Basin. I think it's a great proving ground of technology here in Canada. We've got a wide range of well conditions and a number of challenges, deep, hot wells, direct steam injection, lots of cyclic loads. So it's a great place, I think, to prove technology that could potentially be used in the geothermal world. A number of kind of previous presenters have already touched on this, so I'm really not going to dig into this in any detail, other than to say that kind of mechanical properties really play an integral role in determining cement performance. And of course, this is on the assumption that you've managed to do everything else correctly, right? You've managed to place your cement properly, and you've optimized all your slurry properties and everything else. So all the technologies that I'm going to be talking about today, these are fully commercialized technology. This is everything that's been actively pumped in the field at the moment. We've done the optimization of the slurry properties and seen it all the way through to completion. So I did want to talk a little bit about, kind of what are those mechanical properties. Certainly in the oil and gas industry, I think this is an area that isn't particularly well understood. For a long time, everyone focused on compressive strength. That's just, one point on a stress strain curve. And, an important point here is that, that's the maximum point on that stress strain curve, your maximum load. But yielding of the cement is going to occur substantially before that. And when you start to have that yielding, you're going to be having plastic and irreversible deformations of your cement. And that could potentially lead to challenges. We like to talk about Young's modulus, and that's your elastic range. That's where, before yield. And so, certainly you want to typically have a nice low Young's modulus. But ideally also extend that Young's modulus out so that you're maximizing your elastic range and minimizing that plastic deformation as well as you can. And kind of one of the big downsides of cement really is that typically its tensile strength is unfortunately quite low, generally in and around that 10% of your ultimate compressive strength. So certainly that's a challenge, and you can quite often see a lot of tensile failures due to high hoop stress because you've got low tensile strength in your cement. So that's certainly been something that we've focused on. So how is this collected? How's this testing done? Typically you're using triaxial load frames. You can normally just do it under a uniaxial load. So that's where you're just simply applying direct axial load and crushing a sample. This is relatively fast and simple if you have a load frame. You can do an indirect splitting tensile test here. This is known as the Brazilian method. So essentially, while this looks a little bit funny that you're still kind of crushing a sample and not necessarily pulling it apart, the way that you are actually applying load within that is under tension. And so you can actually quite readily get tensile strengths without having to do the complexity of pulling on something. So you can certainly, do triaxial tests as well. Under real well conditions, you do have, the three axes. You've got your confining pressure and your pore pressure as well. In a commercial lab like this, where we're, trying to find the best value solutions, it's been pretty challenging because these tests are very, very slow and difficult to do. Typically, we're engineering these systems to have incredibly low permeability wherever possible. And this triaxial testing is heavily dependent on pore pressure control, so it can be difficult to get accurate results if you're going to be doing that. And just to add another challenge, the testing standards aren't particularly well defined on these mechanical properties testing, especially in the oil and gas industry. And so we've always gone off your ASTM standards for your construction industry is kind of a good place to start for when you're developing and doing your own testing in situ. So, what sort of properties are ideal? So really you want to have, low Young's modulus, a high degree of flexibility, moderate compressive strength, and, as high of a tensile strength as really possible. But the real difficulty here is that all these mechanical properties are very, very highly correlated and related to each other. And if you have a look at the scatter plot that I've got there, this is kind of a couple hundred kind of tests that we've done in the lab here. You can see a strong correlation between your Young's modulus and your compressive strength. And if you pick the other properties, you would see a similar correlation. So it's very, very difficult with conventional cement designs, to lower the Young's modulus without also sacrificing the compressive strength or the tensile strength. And so, it's good not just to focus on an individual property, say, hey, we've got a nice low Young's modulus, but kind of look at all those parts working together. And one way you can do that is actually look at those ratios of, your tensile strength to your Young's modulus or your compressive to your Young's modulus to show that you're getting an enhancement, kind of a disproportionate enhancement of one property, without sacrificing the other too much. And kind of if you look in the range here on the scatter plot, an ideal range, as I said, would be a nice low Young's modulus and kind of moderate compressive strengths. So what options are there for achieving this? And we've seen a lot of great talks already on this, essentially using a composite materials approach, where you can add a second material to your cement to try and impart some of those characteristics of that material onto your bulk cement. Elastomers have been widely used to enhance the Young's modulus. But one of the difficulties there is typically the Young's modulus of your elastomer isn't that vastly different to that of your cement. And so you typically have to add very, very large loadings to try and get substantial changes to your cement's Young's modulus, and that can sometimes impact the potential value to the client. Fibers offer, one potential advantage because they have substantially higher tensile strength than that of cement, often orders of magnitude higher, so you can get away with adding very, very low loadings of it and get substantial enhancements in tensile strengths. And, to give some examples of this, and I've got the reference to the relevant SPE papers that we've published previously on this in each of the kind of bottom right-hand corners there. We were able to enhance tensile strength by more than 50% in a conventional thermal cement blend by very, very low loadings, by only adding 0.5% by weight of blend. And I won't go through all the slurry properties and everything else, but essentially what we saw is that there's no difference in the slurry properties, no issues there, and no change to the other mechanical properties at all. So we're not sacrificing Young's modulus to do that. We saw good improvements in the ratios of tensile to Young's modulus and tensile to compressive strength. And that's kind of one important thing is when you're doing this work, it's important to think of how this is actually applied in the field. And so, we spend a long time working with our operations team and going out to the field and the bulk plants to make sure that we can make this work. And the best solution in the lab wasn't the best solution overall. There was a compromise there to make sure that we could actually get something that was pumpable and workable in the real world. And so that's where it's really critical to have a great collaboration with your operational team to make sure that you can get this technology kind of implemented. When you're trying to optimize this composite approach, and the previous talkers have touched on this already, you really need more than just good individual properties. You really need to have strong synergy and good interactions between the two materials. Obviously carbon fiber, if you're thinking of tensile strength enhancing materials, is something that's widely talked about, widely used in a number of different industries. But when we actually looked at it, it proved to be very ineffective. And so despite the fact that carbon fibers have ultra high tensile strength, certainly many orders of magnitude higher than that of cement, the surface chemistry wasn't compatible with that of cement. And so we didn't get good bonding. And rather than the carbon fiber enhancing the strength of the matrix, it would just pull out. And so we didn't get enhancement of those properties. So certainly that's something that's really it's worthwhile paying a lot of attention to make sure that you've got good enhancements there. So when you're looking at your graphene, your boron nitride, whatever it might be, to ensure that you've got strong interactions there to maximize the potential. And so, continuing down this path, we've been really kind of interested to try and understand how these composite materials are impacting and changing, failure. As I said, the ultimate compressive strength is just one point on a curve. What does that yielding look like? So we did a collaboration with the University of Alberta, kind of doing small scale replicating a wellbore scenario where we had a cement sheath to scale around a piece of casing that we're able to pressurize and induce stress in that casing. And then we coupled this with direct image capture, so we're able to do high resolution imaging and direct strain mapping of that surface and actually directly follow the buildup of strain on that surface and follow where cracks initiate and propagate through the material. And kind of the animation that's playing there in the bottom right corner is just showing how the strain is propagating through and we're getting a failure as a function of different pressure inside that casing, which is inducing obviously a hoop stress in the cement. The top sample there is a standard thermal cement without any fibers, and the bottom one is with the addition of fibers. And kind of a couple of things that you see here is that we do get an increase in the total failure load, approximately 28% increase in the pressure at which failure occurs, and also the appearance of slower crack propagation. You can kind of see that at the top image, that crack seems to propagate quite quickly across the screen, whereas in the bottom image with the fibers, that seems to be a slower, more ductile process. And I say the appearance of slower crack propagation, anyone who's done failure analysis would know that cracks should spread incredibly quickly and certainly way beyond the speed that we would have been able to capture in the test setup that we had. And kind of what we really think here is that there's some complex failure processes occurring that's leading us to be able to actually follow this process and kind of see it occurring. So, continuing to build on this and really try to understand what is this, complex failure process, what does cement look like post-yield? This is especially a problem for us dealing with cyclic steam injection, where we have clients potentially injecting steam all the way up to 340 degrees Celsius, 640 F. At that point, your casing is yielding. That's an accepted thing in the industry here. And I guess the question I propose to the audience is, if your casing is yielding, what hope does your cement have? And so, does it make sense to try and engineer a system not to yield? Is that the best value? Can a more ductile cement system provide a better way of delivering integrity and value at the same time? Because, if you look at one of these stress strain curves, at what point has this cement failed? I think that's hard to determine. And if you look at the civil engineering kind of area, and just a kind of a picture of a bridge that I took kind of locally here, potentially they're okay with localized cracking and maybe some surface some surface defects and local yielding, as long as the function is still there and they understand kind of the network of cracks and what's going on there. The challenge is the subsurface is more difficult to understand. It's kind of dark down there, right? So, what tools do we have for trying to understand how yielding might change integrity? And if you're thinking of integrity, really it's own isolation, and I think that comes down to permeability. So we can prove maybe that we still have low permeability. Do we still have integrity? And that was something we're really wanting to look at. So taking a similar approach to the previous presenters there, we're applying different axial loads to cement and then imaging them with micro CT, looking at the microstructure there, the potential communication pathways, and modeling fluid flow through that. So we're just comparing, a conventional cement and again a cement with a fiber additive. And you're starting off, zero stress. This material has a permeability of 0.1%, 0.1 millidarcy. And if you take that material up to point E here on your stress strain curve, you've over doubled your permeability. And I think most people would have probably expected more, and we certainly expected to see more permeability change as well, considering the fact that this material had traditionally failed. But when you actually look at the micro CT analysis, you can see that you've got localized cracking, but that there isn't an interconnected pathways of cracks. And then, by comparison, when you look at a more ductile cement, a cement that's got these fiber additives, and it's taken to the same strain point, that's point F2 here, and see, the micro CT analysis, no real indication of cracks or defects being observed there. And, this is down to resolution of around, 10 to 15 microns. So we had pretty good ability to see cracks that were going to be contributing to permeability changes. But yeah, when you then look at the fluid flow, you can see that you don't actually really see any significant change in your permeability relative to the original sample with no strain. So yeah, certainly an interesting concept that we're looking at there. And so the question goes, can we push this further? Can we look at other types of composites? And I wanted to share an example that I thought could be relevant to the geothermal world. Obviously, there's always a lot of challenges with losses. Certainly, we see the same thing on the thermal side as well. So there's a desire to lower the density of these blends wherever possible. Certainly, you can go down the conventional route of using, typical extenders, but typically you have high permeability and poor long-term properties there, and it's difficult to get, cement densities below your 1,300 kilograms or 11 pounds per gallon. Foam cements have already been kind of discussed a little bit. They've got a number of advantages, certainly exceptional at preventing and mitigating losses and excellent ability to withstand mechanical stresses. But on the other side, they do have a high degree of operational complexity. It's a lot of extra equipment out there, and they can be quite sensitive to contamination, and you need to be very, very vigilant with your cement blend design to ensure that you've got a robust slurry system there. A potential alternative to foam cement, maybe with some of the advantages still, is to use these glass microbubbles. And if you're not familiar with those, these commercially available hollow glass spheres, low specific gravity, substantially below 1 specific gravity, quite small, sub 100 microns sort of thing. And so, some advantages there is operational, quite simple. This is a conventional cement design, no extra equipment required to pump it, and similar to a conventional cement, minimal sensitivity. There are some potential downsides is chemical stability, especially when we're dealing with the sort of high temperatures that we deal with on a normal basis. And kind of just giving a high level summary of some of the properties that we observed when we made this lightweight cement, and this was a system down to about 1350 kilograms per cube, or just over 11 pounds per gallon. And these are mechanical properties after 1 month at 340 degrees, 650 F. So still, maintaining an excellent compressive strength, very nice low Young's modulus 3.2, a high relative tensile strength, certainly substantially above that 10% of compressive that you typically would expect to see, and a nice low kind of ratio of your Young's modulus to compressive strength. And these properties, are pretty comparable to that of a foam cement. So really a nice ideal combination of properties there. And of course, whenever we're looking at this, we're always looking at the X-ray diffraction analysis as well, making sure we've got the desired phases, which in this case is zonolite. This is kind of like there's a question about talking about failures. I do want to talk about the failures we had here. This was not an easy project. We went into it kind of assuming that things would be relatively straightforward. It took a number of iterations of blend design to actually get workable slurries that were stable at high temperature. And the assumption that these glass microbubbles are inert certainly does not hold true when you're dealing with temperatures of 340 degrees Celsius, a couple of thousand PSI confining pressure, and highly caustic conditions in your cement, like pH 13. Under those conditions, there's not many materials that are chemically inert, and that's certainly what we saw. And it took a number of iterations and optimizations and collaborating with the manufacturer of this to get a system that was thermally stable, long-term, and robust. So, yeah, certainly, everyone likes, as we say, I like to talk about our successes, but this one was a tough nut to crack for sure. So a couple, additional blend benefits that I wanted to share with this group. Shell did some excellent work a number of years ago looking at ways of mitigating trapped annular pressure. This can just be pressure that builds up behind the casing due to the thermal expansion of water, or that water flashing to steam as you're heating it up. Typically associated for us here in Canada with direct steam injection. And basically, so the downside of trapped annular pressure is that you can readily collapse your casing. And so some of this work done by Shell was actually showing that by including these glass microbubbles, you were putting a kind of a stress dissipator within your cement, that high pressure had a place to go. It could collapse these bubbles because they are hollow and they've got a vacuum inside them, and dissipate that trapped annular pressure and mitigate against casing collapse. And they had high degrees of success with that. Also, since you are in, you've got these hollow glass microbubbles, we do see a substantially lower thermal conductivity, 28% relative to that of a traditional kind of thermal Class G cement. So, I thought that could be interesting. Maybe there's some potential to improve thermal yields in steam injection, or on the geothermal side, potentially an advantage here for these systems. So finally, validating performance. I think it's interesting to talk about, yielding not impacting the bulk properties or bulk permeability. But realistically, I'm not sure if the bulk cement is the path of least resistance when it comes to loss of integrity. I think the interfaces are what really needs to be looked at, and especially the cement casing interface. That's not a strong interface. That's typically a mechanical interaction predominantly, and really, one of the main ways that the failure mechanisms can occur. So in the late stages of commissioning and utilizing a validation cell. So this is a kind of mini wellbore replica. We were able to replicate the downhole temperatures and pressures for primary or remedial cement applications. So looking at cement in the annulus or cement plugs, and being able to follow the permeability as a function of time here as well. And of course, looking at cyclic loading of temperature or pressure as well. and just, it's kind of just showing some of the pictures of the setup that we've got. This is a couple of foot tall, just to kind of show the scale. So this is kind of an exciting tool, and I guess stay tuned. We're going to be presenting some SBE papers in the next little while about some of the exciting results we're starting to see with that, with validating the approaches that we're using here.
Well, very good, Simon. We have time for a few questions.
So can you hear me?
Yes.
Hi. So I have a question about the fibers that you were talking about. Do they have any surface functionality or any surface treatment to have some kind of chemical compatibility, chemical interaction with cement components?
Yes. Yeah. I mean, so they are a synthetic organic fiber, not your traditional inorganic materials. We found that those decomposed too readily in a thermal cement matrix. But yes, there is essentially a coating on that allows for good and strong bonding of the cement to that surface, and also for those fibers to be dispersible. Certainly anyone who's dealt with fibers for a lost circulation application, if you're not getting a product that's well dispersible, you can end up making a horribly nasty lumpy cement. So yes, there are coatings on that just to make sure that we get good synergies there between the cement and the fiber.
Thank you.
Yeah, I also had a question about the fibers. I know you're most likely using the ones that have a higher degradation temperature, but even those only go up to like 300 degrees Celsius before their melting point. And I know as an industry, we're pretty lacking because we can't do in situ testing at these higher temperatures. But I was wondering if you maybe cured at the higher temperatures and then did the tensile testing to make sure the fibers were still intact.
Yes. Yeah. And yeah, so I didn't have the kind of time to go into great detail on that. If you look back at that original SBE reference, we did ultra high temperature curing on those, scanning electron microscope analysis all the way up to approaching 700 F, the limit of cement, Portland cements. And so I would say yes, traditional fibers melt, but if you understand the chemistry and potential decomposition pathways, again, yielding or failure doesn't mean that you don't have performance there. So again, it's a case of some complex chemistry going on, but by understanding that, we were able to make sure and validate that that product was still stable at those steam injection temperatures.
Oh, perfect. Thanks. Second question, were you able to look at different aspect ratios, lengths of the fibers to maybe optimize?
Yeah, and that's kind of what I was alluding to there, talking about, the field application and real world performance versus the lab. The lab showed better performance with shorter fibers, so you could get a higher fiber count. But operationally, that was just more challenging. And so, the compromise there, we still got 90% plus of the performance with a longer fiber, and just more operationally straightforward. So, yeah, we did spend a lot of time looking at different aspect ratios. One thing that's important to look at, if you go for very, very long fibers, your slurry properties can start to look very bad. You get very high viscosities and bad mixability, and it's hard to disperse them. So, typically we focused on, shorter fibers, typically less than 5 millimeters sort of thing, to make sure that we could get good slurry properties and still get good tensile strength enhancement.
I have to apologize. I think I advanced too quick on Simon to finish up a summary of his speech. So if you'd like to go through that.
Yeah, so just
questions.
Yeah, just quickly. I think we all know, geothermal wells and thermal wells subject these wells to a high degree of stress. There's a complex balance of priorities here. There's no silver bullet. There's no one solution. But I do think, using the composite approach, if you make sure there's good interactions between your systems, is one way that you can enhance these performances. And I think we'd like to propose this idea that localized cement yielding doesn't necessarily mean a loss of integrity. And if we can start to understand yielding, then I think we're going to be able to deliver integrity at and improve value for our clients. Because at the end of the day, if these products aren't commercially available, if they're too expensive, unfortunately, clients aren't willing to always pay for that, right? So if we can deliver value here, then I think that's a good way of improving integrity. And I do want to, quickly just thank our collaborators here, and finally, just the organizing committee. We've faced our own high stress environment in the last few years. So thank you for persevering and being ductile and letting us still be able to present and share in this excellent workshop. So thank you very much.
Simon, thank you, Mark. I have a question and a comment, and one of those questions is rhetorical. So I have two questions. So let's start with a comment. I've noticed a lot of testing, actual testing. Maybe I missed something here, Simon, but I did not see any confined testing. If you don't perform confined actual testing, you cannot determine a friction angle. If you cannot determine a friction angle, you really neglect your ability to study shear stress. So maybe I missed something, Simon, but have you performed any confined testing to determine friction angle, hence shear testing or shear values or shear stress? And one of the rhetorical questions is, if I want to lower the Young's modulus, shouldn't I just add more water to the system, lower the density? I'm going to lower the Young's modulus in a very cost-effective way. And the second question I forgot what was an ask.
Yeah, so in regards to that confining test, we have done confining tests in the past. When we are trying to screen materials under a relatively high throughput environment, we found that there's relatively good correlations with the uniaxial testing. And so, yes, you can do the triaxial testing. As I said, there's a high degree of complexity there. And so that's, something we typically do last minute, kind of the last step, but I didn't share those results. As for, lowering your Young's modulus by just adding water. So as I said, all those properties are highly correlated. If you lower your Young's modulus by adding water, typically what you also see is a disproportionate reduction in your compressive strength and your tensile strength. So maybe you get a 50% reduction in Young's modulus, but you might get a 70% plus reduction in your compressive and tensile. So that's kind of where the sum of everything together is important to look at. It's possible to do it that way, but typically that doesn't get you the total package of properties that you really want to look at.
Very good, Simon. That's a very good presentation.
Thank you.
Okay, coming up for our third presentation is Carlos Fernandez, and he will be speaking on self-repairing polymer modified wellbore cements with high thermal and chemical stability for enhanced geothermal systems. Good morning, Carlos. Can you hear us?
Good morning. Yes. Can you hear me?
Yes. Yes.
Fantastic. And can you see the entire screen or just the computer's version of?
I can see the screen.
Okay.
From here. Yes, we're good.
Okay. All right. Thank you very much for the opportunity to talk about the work we have been performing for now 6 years with Geothermal Technology Office funding and some LDRD funding internal from Pacific Northwest National Laboratory. So I gave a talk a few months ago and presented some of the work that the original work that we started back in 2016 on the introduction of polymers to cement slurries to bring about self-healing capability to cement. And now here we are going to present some additional results that we had in the second part of the project. But first of all, let me just see if I can, there we go. So this is the team. It's a collaboration between NETL and PNNL with Barbara Kuchko, obviously from NETL, Nick Huerta, former NETL, now PNNL. So he's in our team here at PNNL. And then we have different background, technical backgrounds from chemical engineer, polymer chemists, molecular or computational chemists and technicians and so on. This will be very brief. This is just an introduction of basically cement production and the amount that is being produced worldwide and the impact that has, particular environmental impact with 1 pound of CO2 per every pound of cement. Just wanted to give this an opportunity to for everybody. I think everybody's aware of that, but about, and it's not in this slide, but about 1% of the total cement used in USA, it goes to wellbore cement. So we can obviously reduce the number of interventions that we have to do to replace or repair cement. We will also not only save money, but also be more environmentally amenable with the introduction of, again, new technologies. I think everybody talked about this, particularly in the last two talks, the wellbore failure modes, the bonding and formation, the bonding casing, the shear deterioration that we were just listening to conversation, questions about, and the tensile failure, the radial fractures generated in confined environments. And this is obviously due to the extreme temperatures, up to 350 Celsius, while in ECS, it can be 450 Celsius, in some cases even 500 Celsius, if we're talking about super hot ECS. And obviously the thermal shock and the chemical harsh environments all can introduce any of these failure modes to the cement in the wellbore. So our concept is introducing a polymer, obviously a thermally stable polymer. And if we're talking about polymers, you always think about the integrity of the polymer at high temperatures. So we are looking at polymers that are highly thermally stable, based just on TCMS, polymers that can be stable between 250 Celsius all the way to 430 Celsius we've seen. Some of them are thermoset polymers, epoxides. And the idea here is not introduce a self-healing polymer. In some cases, the polymer itself self-heals. So there is a mechanism. For example, here, this is a thermoset with sulfur-sulfur bonds in the backbone of the polymer. And that sulfur can exchange with other sulfurs in the polymer. And during that exchange, if you have a break of a fracture in the polymer itself, the polymer can mobilize, remove, break this bond, and this has to happen with heat. So if this is thermally activated, and then forming different bond, another sulfur-sulfur bond to bridge that fracture and heal it again. So it's not just a simple self-filling polymer or a self-filling mechanism, but it's actually self-healing, a true self-healing, because you form a chemical bond at the fracture and you restore the structural integrity of the polymer. Well, we thought that if we have polymers that can have different functionalities in the backbone, and that's why I asked the question about the fibers, functionalities that can interact not only with the polymer itself, like the sulfur-sulfur exchange, but also with the cement components like the calcium or the oxygen of the aluminum silicates components or hydrates of the cement, or the calcium silicates hydrates of cement via either hydrogen bonding or coordination bonds or electrostatic interactions such as an alkoxide and oxygen of the polymer, like in this case, you see here an epoxide with an oxygen here. It's hard to see, but it's an oxygen that can, when it's with a negative charge, forming an alkoxide, can interact with the calcium, for example, and form a calcium-oxygen bond. So the idea is that the polymer will, if it's homogeneously distributed in cement, and it can interact with different components of cement in the presence of fracture due to concentration gradient and also pore pressure, capillary forces, the polymer can migrate to the fracture. So debond nearby the fracture, migrate to the fracture, and then bond back to the fracture, not only filling the fracture, but also forming a chemical bond and restoring the mechanical integrity of the material. And that's the concept, and that's this concept is now protected with 2 patents here in the United States, and we'll be looking at different chemistries. And I'm going to just show you a few examples in the next slides. There are other polymer approaches or polymeric cement approaches where they use capsules. Everybody's very familiar with the capsules and the polymer having a catalyst, a polymer backbone, a precursor, and or monomer, and then a cross-linker. And when the fractures basically breaks and open up those capsules, the polymers react, they polymerize, they fill the fracture, but it's actually a noise. It's not true self-healing, but it's actually a filling event where as long as you have enough of the catalyst, cross-linker, and monomers, you're going to have fractures being healed by filling the fracture due to the polymerization and cross-linking of the polymer. In our case, we don't need capsules, we don't need a catalyst. All we need is to have the polymer already polymerized and distributed homogeneously in the cement matrix. And then because it's hot, that polymer will have, particularly when the smaller strands, will have mobility to be able to dynamically and reversibly exchange bonds with the cement, and in the presence of fracture, be able to heal that fracture. So this is a thermoset epoxide, for example, just at 70 Celsius, you can generate with a razor blade a fracture. And if you wait for a few hours, you will, at 60 Celsius, you will see that the fracture is completely healed. The tensile strength of this polymer is very close, if not almost the same as the original. And these polymers, since the bonds are reversible and dynamic is changing at particular temperature, this self-healing can occur over and over again. How we introduce these polymers into the cement slurry. So, and we talked about this in the previous talk, so I will go very fast, but basically you either have monomers as a powder, okay, and a cross-linker also, and you add it and you mix, you make a solid solution of the cement, the pozzolanic material, and the polymer precursors. And then that slurry will cure and form the cement hydrates. At the same time, we will cross-link and polymerize the polymer, forming a very kind of like a mesh of polymer, a cross-linked polymer across the entire matrix. So the polymer will be homogeneously distributed in the entire matrix. If the polymer is not hydrophilic, and you have in some cases like a cross-linker is an hydrophobic material, you can use a surfactant to disperse it and avoid this water segregation and all the problems that you have, like the previous talk was mentioned, that, you know, if the fibers are not compatible, and compatible meaning have some kind of sulfur functionality to be able to disperse in the slurry, you have water segregation and then clumps of fibers, and you don't want that in the final product. Very quickly, at 200 Celsius, I think everybody knows, for cement aged silica flour, the main components are sonolite, portlandite, and scheelite, with some of the quartz in excess. Calcium hydroxide, obviously, portlandite, that continue reacting with with the pozzolanic material to form calcium silicates. We all know that, and we haven't seen in the presence of the polymer that changes, except in a couple of formulations. The polymer in 2 of the 3 formulations that we are going to present here show retarded effects. So in the case of if you measure the consistency and fusion of time, as the material hardens, the consistency increases. In the case of a controlled unmodified material without a retarder, you will have in less than 30 minutes a complete boost of consistency, and the material is no longer workable. So you need a retarder. In the case of polymer cements, and we're talking about 15%, but in some cases we go as low as 5% based on dry cement. You don't need a retarder. The actual polymer itself, the polymer precursor, as well as the polymer acid polymerized, forms what we believe a shell or semi-impermeable shell around the anhydrated components of the grains of the cement, and reduce or retard the hydration process. Eventually, the consistency increases, but you have workability for at least 120 minutes. 90 minutes is what is required for a geothermal wellbore cement. This is a control cement, and these are X-ray microtomography, and you can see here 3 different composites and how the polymer in yellow is homogeneously distributed and even migrate to the interface of the cement casing. This was confined cement with 2 concentric casings, one in the central and another one surrounding. And you can also see that in all cases, the polymer not only is homogeneously distributed in the cement matrix, but also migrate to the surface. And that's also important because if we have interactions with the casing or the formation, you can increase the adhesive strength and the recovery of adhesive strength per shear stress. X-ray diffraction, we did analysis. We took 2 kind of polymers, 2 type of cement H, and also the thermal shock resistant cement that is in the next slide. For cement H, after 24 hours, we see that there are some changes in the patterns compared to the cement without any polymer. For a polymer that is polyethylene coacrylic acid zinc salt, there is no changes. This polymer actually doesn't act as well as a retarder as the other 2, the thermoset epoxy and the BPA combined with the zinc salt. I will not be able to tell you what BPA is yet. But we see some changes in the diffraction pattern compared to cement H for the thermoset epoxy and for this second polymer. And the reason for that is because they act as a retarder, as I showed you before. So after 24 hours, you still see that the material hasn't formed the final schismotite, calcite, catoite, portlandite, and sonolite that we see for other polymers. After 24 hours, 48, or even after 5 days, you end up having all this diffraction pattern being the same as the control cement. But the first 24 hours, there is some retardation even after the first 3 hours that I show you in the rheological properties, and you see some of peaks mean weak sonolite and quartz, so still unreacted pozzolanic material. Nevertheless, for thermal shock resistant cement, which is a cement based on aluminates and silicates, not only silicates, hydrates, but also aluminates of calcium, we don't see for any of the 3 polymer formulations, we don't see any changes in the crystal structure. So don't understand exactly why, but in this case, these polymers may need, this formulation may need a retarder because they, after 24 hours, form the final or close to final products of hydrate cement. So polymer and thermal stability. So the way to do that, we do FTIR, we do thermal total organic carbon, and we also do, and I'm going to present only this, is carbon 13 NMR. Just to look at the thermal stability of the material and the structural integrity of the polymer in particular. And what we see here, for example, for thermoset epoxide, we age this material at 200 Celsius only for 30 days, which is obviously not the 30 years that a wellbore should, average lifetime of a wellbore, but it's a way to say, okay, after 30 days, we still see the polymer. We have some changes in the peaks, even after 1 day, but the changes are due to the interactions. For example, in this case, this ester breaks and form a carboxylate that can interact with the calcium of the cement and form a coordination bond. So there will be changes in the peaks, but that doesn't mean that the polymer is unstable. It's just the polymer interacting with the cement matrix, and that's what we want. So 30 days, 200 Celsius, the polymer is still intact and interacting with cement, and this is for cement H. If we and this is also for cement H. We don't have any NMR for TSRC, but 300 Celsius for the zinc salt BPA cement, 30 days at 300 Celsius, the structure of the cement is, the structure of the polymer is still intact, is interacting, as you can see here, with the calcium as well of the cement. And this is the carboxylic acid of the polyacrylic acid zinc salt. So the carboxylate is a salt, and it changed the the zinc of the salt with the calcium of the salt. And that could be one of the mechanisms, the reversible interaction between the calcium and the carboxylate, one of the mechanisms for self-healing. So after 24 hours, we need, for geothermal wellbores, have a compressive strength above 1000 PSI or 6.9 megapascal. All of these polymer modified cements have a reduction in the compressive strength as compared to control cement H or the thermal shock resistant cement, but all of them have a compressive strength after 24 hours above their requirement, between, I would say, 1500 PSI all the way to 3000 PSI, just after 24 hours. The compressive strength obviously increases as the material continues hydrating over the days. YAM modulus, there were talks about that. Fibers reduce the YAM modulus. We want the material to be more ductile. Yes, for the addition of polymers, even adding 5% of the polymer produce a reduction in YAM modulus by about 1/3 of the YAM modulus of control cement. So the material is much more ductile, but still maintaining the compressive strength required after 24 hours. And for thermal shock cement, which is a more ductile material than cement H with pozzolanic material, still the addition of the polymer reduces the YAM modulus by 30%, and in some cases halfway, 50%, which is again a very important feature of these materials. Why? Because we don't want a material that is brittle, because the fracture propagation is much faster, the fracture propagation rates, and what we want is a material that will reduce the fracture propagation rates and enable in that way to self-heal or have some autogenous healing by continued hydration, some like in the case of materials that don't have self-healing but continue they say heals just because there is still evolving of the hydration products over the years, days and months. So this is permeability. We did also compressive strength. I measured that in the previous talk, but you can see here what I just mentioned in the previous slide. The control cement, particular cement H, when you generate a fracture using it's a modification of the Brazilian test, where you actually put two loads with different one higher than the other one, and you displace this and generate a shear fracture. In the case of control cement, you end up with, because of brittleness, you end up with, in some cases, with material like it looks like this picture. But when you do that with the polymer modified cements, you just displace, generate the fracture, and then you can put the pieces together. And after 24 hours at 200 Celsius in some cases, or 300 Celsius for the second formulation, you end up with the healed fracture. So here, what we see here is the class H cement and the TSRC. These are the control cements without any polymer. And we can see the ratio of the permeability after healing and before when the fracture is generated is higher in all of the control cements. So the permeability is higher even after leaving for 5 days the material to heal. The permeability, the fracture will not heal. We use thermal wrap to keep the pieces together. In some cases, we still have only 2 pieces, but even after 5 days with thermal wrap, 200 Celsius, there is no healing. So the permeability is higher. In the case of TSRC, the same thing. But when you have TSRC after 30 days and you generate a shear fracture, again, no healing, the permeability is higher even after 30 days of healing process. But if you have a polymer, in some cases you have still a permeability that is higher than the original fracture, but is much lower than the unmodified cement. And of course, in some of the cases, most of the cases for the TSRC, for example, we have a permeability that is reduced by 70%, in some cases almost 1/8 of the original permeability. So you can see the self-healing behavior taking place, and it's also by naked eye be able to see it. We have also presented some X-ray microtomography to show where the polymer is located, and you can not only see the polymer homogeneously distributed in the cement, but also that has migrated to the fracture and generated a bond with the fracture, completely filling, or at least nearly totally filling the fracture. Obviously, the reason for these different numbers is because we cannot control the width of the fracture. For fractures to be healed, in these cases, we have been able to heal fractures up to 500 micrometers, so about 0.5 millimeter. 0.5 millimeter is a very large fracture in wellbore cement. First, you generate microfractures before you have this detrimental fracture event. But even with these large fractures, the polymer is still be able to reduce the permeability of the cement in these formulations. We also did some tests for addition to casing, and so what the polymer does when it migrates to the surface of the casing. Does it increase the adhesive strength of the material? Does it not? What happens when you actually fail? So you bring this stem down and then break that bond. And when you reset it and wait for the healing event, let's say 5 days at 200 Celsius or at 300 Celsius, does it recover some of this adhesive strength? Does it stay the same? It never recovered it. And what you're going to see here is, and we can do this over and over again, right? So we use a compressive strength system. We bring this down about half an inch, and then we can reset it and do it again. We can do multiple damage healing events at the interface casing cement in a confined environment. And what we see is, this is class H. So it has a fairly large adhesive strength to begin with, but once you break that bond and you let it heal and you test it again, the adhesive strength is about 1/8 of the original adhesive strength. This happened also with the 2 of the polymers for the cement H, and this was the zinc salt and zinc salt with BPA. But for EPS 25, in EPS 25, the compressive strength is the adhesive strength is original, is statistically similar to the modified cement, but the recovery is significantly higher than the unmodified cement. In the case of TSRC, we start with a very low adhesive strength, but it's boosted if you add either of these 2 polymers, not EPS 25, but these other 2. And then also that you start with a higher adhesive strength, in some cases up to 3 times, but also the recovery ratio is higher, much higher than, and statistically different than the recovered adhesive strength of the unmodified cement. So in conclusion, in terms of rheological properties, a couple of the polymers that we use act as not only as a material that can bring about self-healing behavior to the cement, but also can act as a retarder. So you can reduce the cost of the cement by removing the retarders just because you are in the polymers. But we can talk about the cost in if you have questions, but in terms of adding polymer, because like you know, cement is dirt cheap. It's 5 cents a pound. In some cases, maybe 8 to 10 cents, but still very cheap. So adding anything, fibers, graphene, polymers will increase the cost of the cement, but you have obviously the gain in terms of the stability of the cement and the potential reduction of the number of interventions of the wellbore throughout the lifetime of the wellbore. Mechanical properties, so the compressive strength is reduced, but still above the wellbore requirements. It's about 50 to 70% more ductile, and that's very important to reduce the fracture propagation rates and be able to self-heal. Or if the material doesn't self-heal, allow the cement for continued hydrating and fill those fractures before the fractures become detrimentally higher. The thermal stability, we've seen, I haven't showed this, but the polymers are stable between 60 and 350 Celsius. There is one polymer formulation we haven't tried yet that is stable up to 420 Celsius. Like I say, there's still a lot of work to do. Self-repairing, we have seen in all the polymer cement formulations that there is the ratio of the permeability before and after over before healing event is much lower than the control cements. We also seen in the previous talk that I gave a few months ago, the compressive strength is recovered between 80%, and in some cases it's even higher than 100%, 120%. And this is because there is a combined healing event that is not only due to the polymer filling and bonding to the cracks, but also the continuous hydration of the cement that also fill those cracks and sometimes make the compressive strength even higher than before the damage occurred. Adhesive strength to stainless steel, there were two formulations for cement H. EPS 25 is the only one that brings about higher adhesive strength, similar adhesive strength, original adhesive strength, but higher recovery of the adhesive strength. And for thermal shock resistant cement, the cements based on calcium silicate aluminates, the zinc salt and zinc salt BPA polymers not only increase the original adhesive strength of the material compared to the modified cement, but also the recovery ratios are in between 2.5 and 10 times higher than the modified cement. This is just some information for 15 minutes talk. Obviously, I can answer any questions you may have. Thank you.
Carlos, I like your opinion about cement being cheap. I'm always told that our cements are very expensive, so.
Well,
I like that. So if anybody have any questions for Carlos?
See, here's a question, if I may. Hey, Carlos, thanks for impressive presentation. I attended your presentation last time as well. It is impressive as usual. But one of the questions I would have, I know you mentioned the stability of the polymer between 60 to 350. Is that for pure polymer or mixture of polymer and cement?
Good question. So we did both. We did the polymer alone, and we also did cure some slurries and with 5 to 10% of polymer, and then we put in a tissue. And what we see is obviously the loss of water and bonded water, then water that is from hydration at higher temperatures, and then we see the decomposition of cement of polymer, very similar to the very similar temperatures of the decomposition of the polymer without the cement present in it. So those temperatures are for both, either the polymer alone or the polymer with cement. We would anticipate that the polymer may be more, since it's bonded to the cement, may be more stable than the polymer alone, but the temperature of the composition were very close.
Okay, so and another question is, when you're talking about compressive strength, are you referring to UCA or crush test? I'm saying just a
Oh.
destructive compressive string or using ultrasonic.
No, it's destructive compressive strength. Well, for the self-healing event, you have to be very careful, because if you perform you apply the load fairly fast, and you end up to the point where you actually generate fractures that are larger than a millimeter in size, you will not let this, even with the interaction that the polymer had, the migration of the polymer to the fractures, the self-healing will occur, but it will be partial. So at that point, the polymer that have, I don't think anything will be able to heal a fracture. So what we do is we take the load up to about, to the maximum, and then when we see a decrease of about 10% in the load, that's when we stop the test. And then obviously you can see in sorry, go ahead.
So no, I'm saying I'm just referring to impact of the polymer on the compressive string of the cement. Yeah, that I was wondering about that part. Not really self-healing function.
Oh, okay. So the impact, so the polymers are more flexible, more ductile materials to begin with, right? So when you add that to in a solid solution, which is this cement polymer composite, you will bring down the compressive strength of the material. And I will say probably also the tensile strength, although we haven't measured it. But with that, and it's not a rule of thumb, but usually when you reduce the compressive strength, you see a reduction also in Young modulus. But and we observe that. We observe a reduction between 50 and 70% of the Young modulus. And the compressive strength, it continues evolving. We have measured compressive strength after 5 days, and we see compressive strength in the order of 3,000 psi. But if you do the same thing in an unconfined cement that has a potential to interact with the air, and you have CO2 in it, you have some calcium carbonate form, and you boost the compressive strength to 10,000, 12,000 psi. And yeah, it looks good, but at the same time, those very high compressive strength make the material very brittle, and that's why sometimes I'm against, for example, these people that talk about injecting supercritical CO2 to reduce the carbon footprint of cement. But when you're introducing CO2 in supercritical form in a cement that is evolving and is curing, you're going to form a lot of calcium carbonate, and calcium carbonate is very brittle. So yeah, you're sequestering CO2, but you're also impacting a lot of the mechanical properties of the material.
Real quick question. I might have missed it, but do you have a 35% silica in your cement?
We have a 70-30 silica, 70 cement, 30, and that's just a typical formulation for wallboard cement H or cement G, 70% based on dry mix and 30% pozzolanic material.
Hey, Carlos, got one question from an Oliver Coker who was on a chat. He's asking, do you have any estimates for long-term survival of the polymer in the cement? Most geothermal operators have 30 years in the life of their wells.
Yeah, that's the question. Do we know that, or if we don't know it, can we actually perform any type of test that can give us some type of information about the stability over a long time? We don't know. We haven't done any tests above 30 days, but we can do some accelerated tests. We can put these polymer cements in, immerse in mineral acid pH 1 for maybe, I don't know, a year, and look at the integrity of the polymer using NMR, and also looking at the content of the polymer using total organic carbon tests. That's a way to accelerate the aging and maybe have an idea of how it will behave. If you have it for 1 year in acid, that could be equivalent to, I don't know, 10 years on a less harsh environment under geothermal wellbore. But something that we haven't done, obviously, having a power reactor subject to mineral acid for a year, maybe you end up with a lot of corrosion in the power reactor, even if it's castor oil or whatever. So the short answer is we don't know. 30 days, the material is still there. If the polymer at 300 Celsius survives 30 days, I will say, I feel pretty good to test it, at least do some testing the wellbore, at 200 Celsius and and see how the material evolves over time. And that's something that we are planning to do. We just got awarded a technology commercialization fund with 3 industrial partners. And what we're going to do is bring the samples, some of the samples confined down a wellbore in year 2 at 200 Celsius. And we're going to have them there for a year, and we're going to retrieve them every 3 months to do mechanical testing and see if there is any self-healing behavior after 1 year. More than that, yeah.
Hey, quick question.
Yeah.
Short answer. This is Jeff Landry here.
Mhm.
The geothermal wells are, you're having losses and breakdowns in the seam sheaths a lot higher in the well than just the hot part. You mentioned that 600C was looked at, but what's your data on the self-healing properties at the lower temperatures?
We haven't tested cement at temperatures below 200 Celsius. What we anticipate, and this is again just hypothesizing, since the polymers some of the polymers have mobility and have self-healing behavior on their own at 60 Celsius, I would say that for wellbores that are at temperatures below 200 Celsius, we still would have self-healing behavior, particularly with the EPS 25, which is a thermoset epoxide that heals alone at 60 Celsius. Now,
Carlos, I'm sorry, we're going to have to probably stop. We've run way over our time here.
No problem.
If anybody has any other questions for Carlos, I'm sure maybe we could arrange either an email or some type of another communication here after the presentations.
Absolutely. Feel free. And I can share the presentation as well.
Okay, well, very good. I want to thank the presenters in our module here this morning. They were all very, very well done and very interesting. And with that, we're going to adjourn for lunch.
Thank you very much.
Thank you.
Our Geothermal Technologies Office has been investing in developing and deploying geothermal for decades. And we've asked Congress for $57 million more for this program in the upcoming year.
This is the Allen S. King coal-fired power station. It produces 600 megawatts of steady, reliable baseload power. Shutting down this power station is the right thing to do, as we've got to stop burning fossil fuels and save our Earth. The problem is, we can't replace this power with just wind and solar. In California, the Public Utilities Commission has finally and formally recognized this problem and has now called for 1,100 megawatts of firm and renewable 24/7 electricity generation by 2026. That's geothermal energy.
We're learning from both successes at the state level, like last year's California Public Utilities Commission procurement decision that geothermal rising helped to boost. And we're learning from our international work, obviously, like Europe's progress on district heating systems. In April, we announced $15 million for geothermal research projects in West Virginia as part of our investments in job creation and economic opportunities in the hard-hit coal and power plant communities area.
WVU Morgantown campus has been identified as a priority location for deep diffuse geothermal project. Therefore, to perform a geothermal resource quantification and risk assessment, an exploratory well will be drilled by a depth of 15,000 feet, along with a full logging and coring program. We'll be using state-of-the-art drilling technologies for this exploratory well. The project will have implications beyond West Virginia University campus. It will provide data for geothermal resources for other potential sites in the Middle Appalachian Basin that has similar geology and demonstrate geothermal energy is a national resource but not limited to Western states.
Department of Energy sees geothermal as a crucial tool to help us tackle the climate crisis, to deliver 40% of the benefits of clean energy to disadvantaged communities, and to build a skilled, diverse energy workforce.
The newly formed Diversity, Equity, and Inclusion Task Force has been very busy since we formed 7 months ago. Our first goal was to create a DEI statement that shows Geothermal Rising's commitment to improving diversity, equity, and inclusion across the geothermal community. Geothermal Rising is committed to improving diversity, equity, and inclusion to provide a brighter future for Earth and all its inhabitants. Our organization and community embrace and celebrate our members' differences. It is a responsibility of Geothermal Rising to encourage and promote diversity, equity, and inclusion. As a global geothermal nonprofit organization, we are committed to connecting the geothermal community. There is more work to be done, and as we expand across markets and internationally, Geothermal Rising will continue to seek equitable improvement to elevate the geothermal community.
The infrastructure investments that are in President Biden's Build Back Better agenda are going to turbocharge geothermal energy in America. We're talking about the biggest investment in clean energy and transmission in history. So my message to you is this: when it comes to geothermal, America is open for business. We are so ready to partner with you to get this done. We are grateful for your tireless work to elevate this important, clean, and reliable energy source. And we're grateful for your willingness to train the next generation of geothermal professionals. And we are excited to secure policy wins all across the country. So thank you so much for inviting me to participate. I hope you have a fantastic conference.